Hello. 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 No. No. So thank you all for coming to Baltimore, to Johns Hopkins for DeepMath, and welcome. So I am Soledad. I'm an assistant professor here in Applied Math, and I'm one of the co-organizers of DeepMath, and I just wanted to thank you all for coming and welcome to Hopkins. And okay, so I was asked to give the introductory remarks for this conference, and they told me that I should start with a joke somehow. So I am not very good at that, so I asked ChatGPT to give me a joke for the introductory remarks at the conference on the mathematical theory of deep learning. And they said that I should say something like, you know that you're a math conference when you're trying to solve for y in y equals mx plus b instead of just predicting it. Okay. I think there's some interesting material that I can work with here. So I changed it a little bit and I said, well, maybe something like, you know, you're at a math conference because we're still trying to understand problems of the form y equals ReLU of mx plus b, which ChatGPT said that I was going to get a chuckle because ReLU, it was a very smart thing to add there. Okay, so that's for the comedic part of the talk. And now, where are we in the mathematical theory of deep learning? What are we going to hear from our amazing speakers today and tomorrow. So we're going to hear about diffusion models from Holden and UHG. We're going to hear about robustness from Nina and from Aaron. We're going to hear about symbolic reasoning from Tom Goldstein and transfer learning dynamics from Sanjit. We're going to hear also about graph learning from Luana and over parametrization from Vidya. So we have a lot of interesting mathematical directions in the theory of deep learning and machine learning that we're going to hear about today and tomorrow. So I'm very excited for the rest of the talks we're going to have. And the schedule is on the website, and also we have some paper schedule that we gave around. So just a few housekeeping details. So there's going to be coffee and water and juice in the main hall, but the food at lunch and the pastries for breakfast are going to be in a different part of the building, which you can just go through it. You don't have to go outside, but you take the right here and then you take a right. You've seen it. I see some of you have it already, so you know how to get there. If you have any questions, please ask me or other organizers. So that's for the lunch. The poster session is also going to be there where the lunch is going to be served. And then you should probably bring your food here because we have tables and all that. And what else? So the poster session is going to be today at 5, and there's going to be also appetizers and some other drinks. And that's it for the schedule. And finally, I want to thank you all for coming and for being part of this research community. Special thanks to our sponsors, and especially to Veronica and Sydney, who are there. And without them, this wouldn't be possible. So thank you so much for all your help in organizing these amazing things. So that's it. Thank you.
Good morning, everybody. My name is Jeremias. I'm an assistant professor in BME, in biomedical engineering here at Hopkins. I'm also part of the organizing committee, and I'm thrilled and honored to kickstart the morning session. To begin, we are going to have Professor Nina Balkan, who is the Cadence Design System Professor of Computer Science at Carnegie Mellon. Nina has a very long record of amazing contributions in theoretical machine learning, in computational game theory. She has received many different awards. Among them, she's a Simons Investigator, and she's the recipient. Alexa wants to contribute. And she's a recipient of the 2019 Grace Murphy Hopper Award of the ACM. So Nina, thank you so much for coming, and we very much look forward to your talk.
Yeah. Yep. All right, so thank you for the invitation. So I'm excited to be here. So my talk is on robust and reliable machine learning. And actually what I'm going to talk about applies to any type of machine learning model, including deep learning. So, but not necessarily specifically to deep learning. Yeah, cool. So let me start with a high-level kind of overview of my presentation. So most of the existing theoretical work in robust machine learning, I mean, there is a long line of work in learning with noise and robust machine learning, but most of it existing theoretical work has been focusing on designing and analyzing machine learning algorithms that somehow achieve nearly minimal error rates on average. However, recent applications of machine learning highlight the importance of designing learning algorithms that are also reliable. And by reliable, I mean they make predictions only when the predicted label is guaranteed to be correct and otherwise abstain. Okay, and so in this talk, what I'm gonna try to present is work on on formalizing the question of how do we design learners that are both robust and reliable. And I'm gonna be thinking about challenging environments, for example, training time, poisoning attacks, or test time attacks, or distribution shift. Okay, so that's kind of the high-level one-slide overview of my talk. And now I'm just gonna go into more details. And actually, I'll mostly be focusing on, just to go back, I'll mostly be focusing on supervised classification, so in particular binary classification to make things simple. And first, I'll start with a just very quick, a couple of slides review of the classic traditional learning theoretic formalization of supervised machine learning, right? And again, here in this setting, the learning algorithm receives labeled examples only. For example, email messages labeled as spam or not spam if we're trying to do spam detection, or could be objects labeled as chair or not if we're trying to do, say, chair detection. So classic fully supervised machine learning. And then from a formal point of view, in the classic learning theoretical models, in the so-called distributional learning theoretical models, we assume that there is some distribution over the space of examples. And then in the training phase, the learning algorithm first gets a random sample coming IID from this distribution. And then this random sample is labeled by an expert according to some fixed unknown target function. And then this is given as an input to a learning algorithm, which then produces a classifier that is then used to classify new examples coming from the same distribution. Okay, and the classifier can be of any form, for example, DeepMath. And so kind of more formally, so in the classic learning theoretic formalization of supervised machine learning, we assume that there is a distribution over the space of examples. And then we assume that in the training phase, the learning algorithm gets to a training sample, and this training sample is drawn IID from this fixed unknown distribution over the instance space and labeled by some target function, which in my talk I'm going to call F star. And then the goal of the learning algorithm is to then do some optimization over this training sample in order to find a hypothesis that has small error rate over the whole distribution D. Okay, and I want to emphasize that here the error rate is defined on average. So in the classic supervised machine learning, the error rate is defined on average over new random points coming from the same distribution. So in particular, the error rate of a classifier H with respect to the fixed unknown distribution, the fixed unknown target function F star, is the probability that my function H predicts differently from the target function on an example drawn at random from the distribution. Okay, so this is kind of an average notion of error rate. And now there are a couple of cases now, or not cases, but a couple of formalisms. So the classifier that the algorithm finds comes from some hypothesis space, and in my talk I'm going to call it H. And again, this can be, for example, the space of deep networks, or decision trees, your favorite types of classifiers. And there are kind of two simple cases that we typically talk about. The first one is the realizable case, where the target function truly belongs to this hypothesis space. So our modeling was perfect. We put down a hypothesis space that does include a target function, And in this case, we hope to find classifiers that achieve arbitrarily small error rates. Okay, and then the second case, which is more realistic potentially, is just diagnostic case, where you just assume that the target function itself, f star, is somehow close to some function in the function class. And then in this case, our goal is to somehow output classifiers whose error rates are, close to the error rates of the best classifiers in the concept space H, or in the hypothesis space H. Cool. And these are the classic formalizations, like if you go back and look at learning theoretic models. Now, throughout the years, there have been actually, people have tried to think about and robust machine learning actually for a really long time, for example, like we used to call them noise models. So, for example, there are examples of classic noise models that people have analyzed within these kind of frameworks. It's a so-called random classification noise, where you, for example, assume that for each example xi in the training set, its label has been corrupted with probability eta, and this corruption is independent of the corruption of other points in the training set. This is called random classification noise model, introduced in the 80s, for example. Other noise models that were potentially even more realistic, but harder to deal with, is something called malicious noise model, where here we assume that for each training point, we corrupted with probability eta, but now we can also corrupt both these features and it's not on the labels. So it's so both the label and the features of any training point can be corrupted with probability eta. And again, so this is malicious noise model, for example, introduced by Valiant in the 80s. And there are other noise models that I'm not gonna put down here, like Tibakov noise and other types of noise models, nasty noise models that people have analyzed in learning theory. But again, in all of those cases, kind of the goal was this goal here. So even if the training data was corrupted, then the goal was to output classifiers whose error rate is small on average over new random points coming from the same distribution. So we still use this notion of error rate in these classic noise models. Okay, however, modern literature in machine learning, in a kind of more applied machine learning, modern literature on robustness, has recently been concerned with so-called instance targeted attacks. So for example, if we're focusing on training time attacks, we're concerned with instance targeted data poisoning attacks, where maybe we have an attacker so these data poisoning attacks. So here we assume that we have an attacker that is trying to modify a training set by adding or modifying somehow the features of a few points, but we do so in order to cause a learner to make a specific kind of error. And this is what people call in recent years in more applied machine learning data poisoning attacks. Okay, so just to give an example. So I'm going to give here a couple of examples. So for example, one would be like if we have a recommendation, in the context of a recommendation engine, maybe an attacker might end up adding a few fake reviews into the training set, and they do so in order to get their product classified positively, but the competitor's product classified negatively. So they really care about their own product being classified well, and they don't care about what happens on average to other products. This is one example. Another example would be, again, a spammer might add a few fake conversations into the training set for a spam detector in order to just make sure that their own spam email goes through. And again, they don't care about what happens on average, to various, emails, whether they are spam or not. Right. So in these cases, again, like in this classic, in this modern literature, like when we talk about data poisoning attacks, often the intention is that an attacker is trying to modify a training set of examples by either adding or modifying a few points in order to cause a learner to make specific kind of errors. Okay, and notice that this is similar to kind of this classic noise models that I mentioned about earlier, like the malicious noise model, except that the attacker's goal is not to raise the overall error rate on average, but to rather induce some specific types of mistakes. And so, for example, the attacker of a recommendation engine just wants their product classified positively and maybe a specific competitor's product classified negatively. And again, they don't care about what happens on average. And so, so now this brings up a question that we thought about is, can we kind of come up with learning theoretic guarantees for this kind of data poisoning attacks, where again, the goal is to induce specific type of errors. And so, like the key question that we had there was, can we provide what I'll call per point correctness guarantees in face of such attacks, instead of thinking about average error rates? Okay, so that's the major question that we thought about. And so basically modeling this situation where where maybe an attacker only cares about specific types of points being attacked. And so, and then, right, and we basically, we introduced a model and analyzed algorithms that is exactly trying to capture this. And actually, the original work that we had was specific to poisoning attacks, which is examples of the attacks that I had in my slides. And so at a high level, the contribution of this work, so it was a Call 2022 paper with my student Ravi Sharma, Steve Haneke, and Darwin Bloom. And so what we do here, we define a notion of robust, reliable learner that provides a strong per point correctness guarantees under poisoning attack. So I mean, at the high level, we even have to change the definition of what's success. And so the very first thing was to basically define what would be, the notion of success here. And so we use what we're going to call a robust, reliable learner. And then we provide an exact characterization of which points can and cannot be certified to be correct with respect to an adversary of a certain power on a given data set. So once we define what do we mean for a learner to be robust and reliable, then we kind of have kind of a tight characterization of what's possible or not possible under this new definition at a high level. And the original work was for poisoning attacks, which again, it's attacks where the attack happens at the training time. So the training set is modified essentially. But we also have more recent work, again, with my students, a couple of my students, Ravi Sharma and Ratana Pogdi and Steve Haneke again. It's coming up in Europe 2023. And here we have extensions of these robust, reliable learners also to test time attacks or distribution shift. But because for most of my talk, I guess actually for all the rest of my talk, I'm going to focus on poisoning attacks. And I want to point out that actually our notion of reliable learners, our notion of reliability actually extends some earlier work. So there has been earlier work in computational learning theory by Ron Rivest and Sloan in called 88, maybe that was the first conference on learning theory in 88. So there was a work on this topic of reliable, useful learners, but it was only for zero noise case, where we have no noise, no attacker. Just, you might want, we introduce the notion of reliable learners and know when they are correct, when they predict and say, I don't know otherwise. But their motivation was more for computational consideration, was not necessarily, this modern motivation where you really have attackers out there to try to mess your learning algorithm up. Okay, cool. And now, so what I'm going to do for the rest of the talk, so that's why I'm going to mostly focus on poisoning attacks, is because I want to go through the definitions. So just because, the major contribution here is to come up with the definition and then prove some guarantees under the definition. And because this conference has the word math in the title, so I decided, well, I can just go and be more mathematically precise here. Cool. So now what I'm going to do for the rest of the talk, I'm going to try to kind of really define what are these robust, reliable learners. I'm going to get mine. Okay, so what is a robustly reliable learner? So a robustly reliable learner for a class H. So again, I'm going to have a concept class H or a hypothesis space H. It's general. It can be anything you want, like deep networks, but let's fix it. And so a robustly reliable learner for a hypothesis class H is a learner that has a property that if it takes as input a data set S prime, which is a training set, which might have been a corruption of the original training set. So my learner is robustly reliable learner for a class H, if given as input a data set S prime and a test point X, outputs both a prediction Y, as in classic machine learning for my point X, but also robustness level eta, with a guarantee that the label predicted is correct, as long as at most eta fraction of the trained data was poisoned, and the true target concept function f star belongs to the class H. So basically, the learner is correct on the point X if the corruption is no larger than an eta fraction of the original training set S, and the target function belongs to the hypothesis space H. Okay, so that's what I call a robustly reliable learner. So it's just, again, it's a learner is correct on any point X, it outputs both a prediction and robustness level eta, and it has the property that Y, the prediction that the learner output is correct on the point X, as long as at most an eta fraction the trained data was poisoned, and the target function truly belongs to the concept space H. And now, given a robustly reliable learner, then we can also define what we call the empirical robustly reliable region. For my learner, given the training set S prime, which again would have been potentially corrupted, and the level noise eta, right? So I have this empirically robustly reliable region for my learner L, the training set S prime, and a noise level eta. What is this? Is a set of points in L, is a set of points, possible test points, for which my learner L, when trained on the training set S prime, would output a robustness level of at least eta. So this is basically the set of points on which the learner is correct if the original data set S was corrupted by a most eta fraction that's leading to the set S prime. Okay. And then this is the empirically robust reliable region, and it in general can be computing given the actual training set S prime. But then we also have what we call the robustly reliable region. And now this is now defined again for a learner that is robustly reliable learner, and an original uncorrupted set S that comes from the original underlying distribution. So that's why I have here S, and the robustness level, noise level eta. And so what is this robust reliable region? Is just for an original uncorrupted training set, uncorrupted set S that comes from the underlying source distribution. For this original set S, uncorrupted training set S, this robust reliable region is just the set of points when no adversary could corrupt, no adversary could successfully attack with a budget eta. So no adversary that can change at most an eta fraction of the points could make us to predict this point in the robustly reliable region incorrectly. Okay, this is what this robustly reliable region is. So actually, yeah. So this is basically this is a set of points so that no matter what the corruption S prime of the original set S is, on these points that belong to the robustly reliable region, right? No matter what the corruption S prime of the original set S is, as long as the corruption is on no more than an eta fraction of the points, the adversary is not able to make us to predict those points incorrectly. Okay, so this is the robust reliable region. Now this one we can compute, the empirical robust reliable region we can compute because we are given text because it's defined based on the training set S prime, which you actually get, which might have been a corruption. This robust reliable region we cannot necessarily compute because given a training set, because S is actually is a set before the corruption happened, but we can analyze it mathematically and we can give bounds on how large it is. Okay, and so now with these definitions, let me give you basically an example of a robust reliable learner. This is actually a generic robust reliable learner. So what is, so the algorithm, so the learner does the following. So it's given as an input, a training set sample S prime and a test example X. And then what the learner finds is the largest value of eta, because the learner has to recall, has to output both a label and a value eta, a corruption value eta for the point x, with the property that if the point is not, the training set has not been corrupted by more than an eta fraction, we are going to be correct on x, on the test point x. Right, so given the training sample S prime and the test example x, what we're going to do, we're going to find the largest value eta such that x, my point x, is still in the region of agreement of classifiers that have empirical error rate over the corrupted sample S prime of at most eta. Right, so basically, just to parse this, so I'm thinking about, so S prime is the actual sample that I use for learning. And again, it's a corruption of a clean data set S, but it's a corruption of a clean data set S. And so I'm going to define here, first of all, here I have the set of functions whose empirical error rate over this set S prime that the algorithm is actually using is at most eta. And when I'm looking at the region of agreement of the set of functions that again have empirical error rate over S prime at most eta, and what's this region of agreement is just the point in the instance space on which all these classifiers in this set of empirical error rate over S prime at most theta, they agree about their labels. Okay, and so again, what my algorithm is going to do, given a training set S prime, which is again a potential corruption of an original data set S, and the test example X, I'm just going to find the largest value of eta such that X, my point X, is in the region of agreement of classifiers that over the actual training, the actual set S prime that I'm using for learning, they have empirical error rate at most theta. And then we output their common predictions, so the common prediction of these classifiers of empirical error rate S prime over S prime at most theta as Y for my example X. And then we add this largest value of eta to be the robustness level. Okay, so this is the algorithm. And then we output eta strictly greater than 0 if no such eta exists. It's like the largest value here is negative, and we just say, we are not able to certify that point, basically. But when eta is greater than or equal to 0, that means we're going to be able to certify the point in the sense that we're going to be able to correctly predict on that point as long as the noise level is no more than eta at the training time. Okay, and I claim that this is a robustly reliable learner. Yeah, and by the way, pictorially here, for example, if I'm learning linear separators going through the origin, then, for example, you can, if you think about it, you have to trust me, but if you think about it, for example, for this point x equals x here, so this is a point here, actually, for this point, we can output the robustness level to be 2 over m, or m, 2 over m essentially, where m is the number of training of all these points here, the training points here. And why? Because this is the largest value of eta, so if eta is 2 over m, then this point belongs to the region of agreement of classifiers that have error rate over the Poisson set of at most 2 over m. But if we go to 3 over m, which is the next level, that's not going to happen. This point is not in the region of agreement of classifiers that have error rate, empirical error rate over S prime 3 over m. So eta here is kind of the largest number we can output. For this point x here, eta equals 2 over m. Okay, and so now we're going to claim that this algorithm is a robustly reliable learner, and to show that it's actually, once somebody internalizes the definitions, the proof is not very hard. So the proof follows from the following observation. So if my learner outputs a label y and a noise level eta, and if the target function f star truly belongs to the high precision space, and if S prime was produced by an adversary that basically has budget at most theta, so has poisoned at most an eta fraction of the training set, then the function itself f star, the target function f star, does belong to the set of functions that have empirical error rate over the Poisson set S prime at most eta. And because by what the algorithm does finds the largest eta such that x is in the region of agreement of its classifiers that have empirical error rate at most eta over the Poisson set, then if you think about it, it immediately implies that for the eta that we output, the label predicted is actually the true label. Okay, so basically we can prove that this is a robustly reliable learner.
I have a question.
Yes.
So is there any assumption about H, because the agreement region might be, so for instance, it might be possible that 10 classifiers agree, for label 0 and 10 classifiers agree for label 1 on X, then in that case, sort of what is the label that you get give X? I'm trying to understand what is the definition of that agreement.
It's of the set of classifiers. So think about all the set of classifiers. So this inside here. So you see it's agree of a set of functions. The region of agreement of a set of functions. In the region of agreement of a set of functions, it's just a set of subset of the instances of those functions all agree about the label. And so and the set of functions here that I'm considering here, I'm saying X is the region of agreement of all the functions, but over the set S prime that we are using for learning, they have empirical error rate at most data. So think about, you are given as an input for the training data S prime, think about all the functions that have empirical error rate over S prime at most data, it's a well-defined set of functions. And then think about the instance, the subspace, think about the points that belong to the region of agreement of those set of functions, right? And then if X belongs to the region of agreement, then you are guaranteed that basically you will be correct on X as long as the fraction of points that has been positive at most data. So that's pictorial here. So I guess here I have, for example, the region of agreement of functions that have empirical error rate over this training set at most 2 over m. So actually this here, these are linear separators going through the origin, and then this will be here, and here I'll have the normal vector of the functions, but over this whole set of examples, the blue and the red dots have empirical error rate at most 2 over m. And then the angle normal vector will belong here, so it will be a subset of functions whose normal vector belongs in either this region here or in this region here. We have empirical error rate, if you look over all this set of points at most 2 over m. And now I'm thinking, what's the region of agreement of this set of functions? Well, here will be the shady region, point either here in the shady region or point in the shady region here. All these functions, for example, will bring the point in here as positive, or the point in here as negative. So we will agree about the label. Yeah?
So yes, and so I get this example with linear classifiers. I guess when you make H a little bit more complicated, the agreement just might shrink to just 0 very fast, right?
Yeah. So I guess for this results to be interesting, so I guess in the end, you're not going to be able to certify points that belong to the region of, given a training set as prime, and we're not going to be able to certify points that belong to the region of agreement of lower or classifiers. And then that set might not necessarily be large. It might be small, but you will be particular guarantee to be correct. So it's not going to be, it might be a small fraction, or like not maybe a constant fraction, the instance rate, or even smaller than that. But you can also prove you cannot certify the remaining data points, because we have a much lower bound. So we actually totally characterize, because you might ask, is this the best we can do? That's exactly what our thinking was. Because actually, if somebody is familiar, we use this agreement and disagreement region in active learning theory, and I've done active learning before, and it's naturally coming there when you think about active learning, you are trying to be aggressive and so on to learn to label. These notions have coming back to each other. And this is when you need kind of concept that think about this problem, kind of like a reliability question once you have knowing, these kind of techniques of using certifying points or being confident about the level of points in the region of the lower classifier gave me an idea, and I was thinking we will do much better. The surprise was, no, this is actually kind of the only type of point that we can do better. If you want to be correct, what is your probability one? Okay, so to summarize what the robustly reliable learner is, because we have a specific robustly reliable learner here, is given a training sample S prime and a test example X, we just find the largest value of eta, such that my point X is the region of agreement of classifiers that have empirical error rate at most eta. So this is a robustly reliable learner. Here we argued it's a robustly reliable learner. You might ask, by the way, because you might ask, well, how do you implement this efficiently? Like, how do you find the largest value of beta such that X is in the agreement region of classifier at empirical error at the most eta? And turns out actually there is an efficient algorithm for doing that. But for any test example X, we can in polynomial time find that largest value of beta such that X is in the region of agreement of those classifier of empirical error at most eta. And at the high level, I'm not going to go for the details here, but what we're going to do, we're first going to find given the set S prime, which again the algorithm uses for learning, we're going to find just an ERM classifier, a classifier that has the smallest error rate over set S prime, over the training set S prime, and then we let Y be the label output by that ERM classifier on my example X, on my test example X, and then we just compute error of X to be the minimum training error of all classifier in the hypothesis space that label X differently from this ERM classifier. And then we just output eta of X, kind of the robustness level on my point X, to be error X minus 1 over n. And you can do an argument to argue that really corresponds to, given a sample S prime, a training sample S prime at this point X corresponds to the largest value eta of X, such that X is in the agreement region of classifies it over the sample S prime have error rate at most eta X. So you can do this, you can implement a robust reliable learner efficiently. The only catch is, that's why this is not yet super practical, is that we have to do this for every test point X. We have to compute this value of eta of X, we have to run this optimization. So this is polynomial time, you can do it in polynomial time, but you have to run that optimization for every test point X. So it's kind of a nice open question to maybe find an efficient algorithm where you don't have to do this for every test point X. Okay, cool. Now, so this is so far I kind of talked about the empirical. I gave the robustly reliable learner, and I guess, and once we have the robustly reliable learner, we can immediately, given a training set as prime, we can immediately compute the empirical robustly reliable region. But you also want to ask the question, which is I think is related to your question. So can you understand the question, given an original uncorrupted training data set, basically, can you characterize basically how large or how small is the region of points that the adversary could attack or could not attack, right? So if we use this now technique, like, yeah, can we characterize basically the fraction of points that the adversary could or could not attack? And so I guess this notion of robustly reliable region is exactly trying to get to this point. So what is a robustly reliable region is basically for an original uncorrupted training data set, this is a set of points that no adversary with budget attack will successfully attack. So no matter how the adversary corrupts a point, we'll still be able to predict correctly on the points that belong to this region as long as the corruption was no more than an eta fraction. I mean, and the adversary could even know the point itself when it comes up, cooks up the corruption. If points belong to this robust reliable region, we'll still be correct on our prediction. And then the question that you want to understand is like, well, how large is this region? And by doing an argument similar to the one that I've done for the empirical robust reliable region itself, we can also come up with kind of, we can also claim that this robust reliable region, given the, for my learner, for the learner that I just described, because I had a specific learner that I described, right? I can argue that the robust reliable learner region for the learner that I just described, given an original uncorrupted training data set and a robustness level eta, I can argue that this region contains all the points in the region of agreement of now low error classifiers over the original uncorrupted training data set. So this robust reliable region for my original uncorrupted training, uncorrupted set S contains all the points in the region of agreement of classifiers that over the original uncorrupted training, uncorrupted set have error rate, empirical error rate at most 2 eta. So basically, in other words, all these points in the agreement region of classifiers that over the uncorrupted training set have empirical error rate at most 2 eta will be correctly classified by my robust reliable learner. Basically, as long as my targeted adversary only corrupts an eta fraction of the points, and no matter what eta fraction of the points it corrupts. Okay, and the proof, again, just flashing the proof by if we internalize the definition, then the proof are natural here. So by triangle inequality, if X belongs to the region of agreement of classifiers that over the uncorrupted data set S have empirical error rate at most 2 eta, and if S prime is an eta corruption of the set S, then X will belong to the region of agreement of classifier that over the corrupted data set they have empirical error rate at most eta. So indeed, when my point X will be correctly classified the robustness level at least eta by my robustly reliable learner that I described earlier, right? By just the definition of a robustly of a learner. Okay, so basically what I'm arguing here that for that specific learner, the robustly reliable region, which again are points that will be correctly certified. So the robustly reliable region given a training data set S that is not yet been corrupted, and the robustness level eta, this robustly reliable region, which are the points that will correctly be classified as long as the other set doesn't use a budget more than eta and the target function belongs to the concept space, includes the points that are in the region of agreement of classifiers that have over training error over the original uncorrupted training data set at most 2 eta. It's actually the original uncorrupted data set, not training data set. The training data set will be S prime. But we have this containment here. So basically, the points, basically at the high level, the points that I can correctly certify, that my learner can correctly certify as long as the budget, as long as my adversary didn't use the budget more than eta, includes the point in the region of agreement of classifiers that over the original uncorrupted data set is that they have error in most 2 eta. But now this brings up the question that you ask, well, is this the best I can possibly hope for? Because if like for linear separators, I showed you in my picture that this can be large, but maybe if I go to maybe DeepMath or more complex classifiers, maybe this region, the points or all classifiers of error most 2 eta agree that region might not be too large in probability measure with respect to the original distribution of examples. So maybe we can come up with a smarter learner, right? Maybe our learner wasn't the optimal one. Turns out actually that we have a matching lower bound. So we can basically prove that no learner can do better than that. So we can prove that for any hypothesis space H and for any robustly reliable learner algorithm L prime that you might think of, this robustly reliable region for my learner L prime, given a set S, an uncorrupted set S, and then robustness level noise eta, must be actually included in the region of agreement of classifiers that have empirical error rate 2 eta over the original uncorrupted set S. So really, that's the best you can possibly hope to certify. If your success guarantee is when you predict you want to be correct, kind of you cannot do better than what we had. But when the learner that we proposed, essentially. Okay, and the proof sketch here is, I'm just gonna go briefly through it. So the proof sketch here is if X, so you're able to successfully certify to predict correctly the label of the points in the region of agreement of classifiers that have empirical error rate at most 2 eta already by our previous learner. So you might wonder, like, there is another learner L prime that might be able to certify points that don't belong to this region of agreement of classifier had empirical error rate at most 2 eta over S. So, but turns out you can prove now that's not the case. Why? Because if X doesn't belong to the region of agreement of classifiers of lower error at most 2 eta over the set S, then there must exist a classifier H0 on H that has empirical error rate over S at most 2 eta, such that they disagree with the target function F star, because F star will belong to this set of points. And now the idea would be, we'll consider S prime to be a labeling of S that is halfway between H0 and F star on the region of disagreement between H0 and F star. And it turns out that S prime will be a legal eta corruption of either H0 on F star, and because of that, a learner, any learner that is required to be robustly reliable learner on input S prime cannot output Y hat, cannot output this kind of Y hat eta hat. This is the proposed prediction, and the robustness level eta hat is greater than eta. Why? Because Y hat would be incorrect for at least one of H0 or F star as a target, because again, S prime is a possible eta corruption of either one. So basically, what we prove here is that, that's the best you can do. So you can really, the only point that you can really certify are the points in the region of agreement of classifiers that over the uncorrupted sample S have empirical error rate at most 2 eta. So that's a type characterization of what we can do here. Say it again. So we'll take the points where they disagree, and some of them label determine half, let's say even, and half of them labeled according to H0 and half of them H0 and half of them labeled according to F star. If you do so, then you can basically then S prime, set S prime would be a legal eta corruption of either H0 as a target or F star as a target.
That's how you get the factor of 2.
Yeah. That's how you get the factor of 2. Okay, so now I so far what I was able to basically give generic results and the generic characterization what you can robustly certify in the presence of poisoning attacks for general kind of hypothesis spaces. Now you might ask, well, and this again goes back to your question, well, how large is the set of points that I can confidently certify, right, given a robustness level eta for specific concept spaces? How large is in terms of the original, in terms of kind of probability mass with respect to the original probability distribution over examples. And here in this paper, in the Call 2022 paper, we've done a computation. We've basically done like, we computed this for the simple case of linear separators in RD when the marginal distribution is a log concave distribution. So here we show that this is a robust reliable learner L, but basically has a property that as for a sufficiently large training sample, it's like of the order d over epsilon squared or something like that, we have the property that with high probability, the probability mass of the points that belong to the robustly reliable region at level eta is 1 minus, roughly speaking, eta squared of d. So actually, the robust reliable learner that I told you already achieves this guarantee, except that we also have a computationally efficient robust reliable learner achieving this guarantee. And this is again for isotropic log concave distributions. Here we use properties of isotropic log concave distributions to come up with this conclusion. So for example, for linear separators, what the conclusion would be is that if the fraction of points corrupted is small compared to 1 over square root of d, or d is a dimension, then an adversary can only successfully attack a small probability mass of the point. An adversary can make us abstain only on a small fraction of the points. And again, we have a polynomial time algorithm, robust reliable learning algorithm for doing so. The algorithm that I described earlier is general, but is not necessarily as efficient. Okay, and I think I'm probably running out of time soon. So 10 minutes. I was, well, yeah, I can have at most 10 minutes, but I don't, yeah, I'll be shorter than that. Cool. So this is for supervised learning, actually, and I'm not going to go through details anymore. Just at a high level, I'm going to mention that we also thought about active learning, because this agreement and disagreement religions kind of computations also come from the active learning literature, technically speaking. And so what is active learning is basically here the learning algorithm aim to reduce label complexity of learning by only asking the labels of a few carefully selected examples from the data pool. And right, and so there is a long literature on this in the classic supervised learning, where I care about doing well on average. And the literature, if you are familiar with it, uses again a region of agreement and disagreement everywhere in the common gap with provably correct algorithms. And it turns out that actually we can just extend those works to basically to basically get a learner that has a robust reliable region that is the same as the optimal passive learner that we talked about, right? Because the learner that we talked about, the robust reliable learner that we talked about, is an optimal passive learner, basically argued, that uses, in the case on the algorithm, uses labeled examples only. And yeah, and we are able to show that we have an active learner that has a property that is robust reliability region is the same as the optimal passive learner, but at the same time, we also reduce the label complexity. So we need much fewer labeled examples to do the learning. Okay, and I'm not going to go through details about this. Okay, so to summarize here, so like the main contribution of this work was really to propose robust reliable learners that are learners that when they predict, they are guaranteed to be correct and they abstain otherwise. And yeah, and what I showed you today was basically guarantees under data poisoning attacks, where the attacker might attack the training set of examples with the intent to induce specific errors. And so, and we are able to characterize the points on which will be correct when we predict even if the attacker induced errors with the test point in mind. If they knew that my test point will be able to be correct, we should decide to predict on that point. And otherwise, but sometimes we do have to abstain in order to get a strong guarantee. So this is what we have reliable learners that are also robust to poisoning attacks. So this is what we talked about today. And basically, I basically showed a generic robust reliable learner that is guaranteed to be correct, to correctly classify all the points in the region of agreement of classifiers, but over the uncorrupted data set S, they have error at most 2 eta, and this learner will be a robust reliable learner against an adversary of budget at most 2 eta. And we show that this is really optimal. It's pointwise optimal. No other learner could do more than that, can certify more than that. And in that work, we also showed basically efficient algorithms, actually how to implement this learner in an efficient way for the case of linear separators. And we also basically provided robust, reliable active learners as well. And as I mentioned, we also have recent work with us that also comes up with definitions for robust, reliable learners, also for like test time attacks and distribution shift. And then, I'm not going through it today because even what do you mean by test time attacks? What's your measure of success? And in the paper itself, I actually have 4 notions of possible measure of success because it depends what the attacker is trying to do to you. And then we have corresponding definitions adapted to these different notions of success, and also corresponding robust, reliable learners that will be guaranteed to be correct on they predict under these different notions of success. And maybe just a couple more comments. So when I started my talk, I kind of put this into context of the context of learning theory, right? Because learning theory has been around for a while, and there's been work on learning with noise and robust machine learning. And I kind of argued how this line of work is a bit different from that line of work, because typically in classic machine learning we care about average error rates, but now we care about when we talk about instance targeted attacks, maybe average error rates are not the right notion of like that we should be analyzing, and maybe what we should really be analyzing are these robust, reliable learners that when they predict, they are guaranteed to be correct, because that's kind of a meaningful notion of success in cases where the learner maybe in cases where the adversary even knows your test point, right? So if the adversary knows your test point and is trying to induce specific error to make you make mistakes on a test point, why would I care whether I output a learner that has average small error rate on average, right? Because I care about my own test point. So, right. So basically, I kind of argued at the beginning of my talk why classic learning theory is not sufficient. I also want to mention that in robustness, because it's been a hot topic in machine learning generally, there has also been more recent work kind of but also try to think about instance targeted attacks, and there are some theoretical guarantees for instance targeted attacks themselves, but for example, this UI paper, but the issue with this kind of more recent work on theory work on instance targeted attacks is that they only gave stability guarantees. They only analyzed when an adversary with a limited budget could have not changed the prediction that was made. But they gave no correctness guarantee. So why would I care if the prediction doesn't change if it's incorrect? So like our major advance here is to also just say when we predict, we are guaranteed to be correct. So maybe to summarize, the prior work on kind of more modern theory for instance targeted attacks was only focused on stability guarantees, which again says analyzing when an adversary with limited budget could not change the prediction. So just stability guarantees, while our main kind of viewpoint here and contribution is to say, no, we want to make sure that when we predict, we are correct. So this is what we call reliability guarantees. And so as I argued, at least for, and actually as I showed you today, for poisoning attacks, and the same thing is true for test time attacks, you can read our NeurIPS 2023 paper for that. We have, I think, optimal algorithms and optimal characterizations of what we can in principle certify. However, the corresponding algorithms are not necessarily the most efficient, and in particular, for every single test point X, I need to do a computation, or like a whole to go from optimization, a non-trivial optimization problem to determine what's the reliability level I can output on my test X. So then I predict I'm confident that I'm to be correct if the noise is normal at that reliability level. So, but an interesting question is whether one can provide more practical computational efficient algorithms or this notion of success, for example, for deep networks? So I think this is a major question that comes from this one. Great, thank you. Yep.
Does efficient here mean efficient production to agnostic learning?
Say it again.
Does efficient here mean like an efficient production to agnostic learning? That means solve ERM problems on noisy instances?
Yeah, so our algorithm right now, yeah, so yeah, I'm going to this is the moreover knows how to do it for every test on that. Can we like for example for linear separators we are able to identify a region where, for example, I mentioned for linear separators we build and work for the identifier of malicious noise and we adapt it to this instance values that access well. For linear separators we are able to just basically say I'm allocating the normal vector of a classifier, and I can guarantee you that all the points that are a certain distance from the classifier will guarantee to be characterized over an identity number. So there we have just a very nice nice description of the robotic dual computation, one time polynomial computation, and then we are able to then say get as output a linear separator with our one-time computation. I'm saying all the points that are a certain distance from this linear separators they belong to the robotic algorithm.
Okay,
so it's a very nice computation that I can do just once at the training time. But our generic robotic reliable learner says for every test point, do some computation. And again, a reduction to ERM, you're right. And then I have to do it for every test time. Test point. I want to do it at training time.
I get that like an ERM workload, but I don't want to run it a number of times equal to a number.
Totally. Yeah, that's exactly what it was.
Thanks. I'm trying to understand how strong the assumption is that F star is in the hypothesis class. So, like, can we loosen the?
Yeah. So right now it's kind of so we kind of what I did is like for realizable case, but in the way for that kind of study, we are complicated as well. But you don't have to modify the definition of what the master reliable learner means. And I'm not sure that we have those with the I think we can like it's very novel question to what are the right definitions. We have already some results that I just found. Yeah. I think that for realizable case, I can confidently say this is the right definition. For agnostic case, we have some definitions. Yeah, it doesn't get an important case of the agnostic.
I have a quick question.
Yep.
So here, the whole assumption about the budget of corruption is on the proportion of the training set.
Yes.
There's no assumption about the extent to those samples that were corrupted, for example, in some norm.
Yeah.
What if you had such assumptions? So, arguably, if an adversary wants to corrupt part of the training set, it's not going to do it with arbitrary corruptions because then the learning test becomes a lot easier. And so, what if I now assume that these corruptions are made to a certain budget in some norm or in some other metric?
Yeah. So
Then can the lower bound be?
No, I don't think that because definitely not enough like that. So the lower bound.
Correct, exactly.
We might not call it so that you potentially get better outcomes.
Exactly.
Yeah, that's another very interesting question. We should add it here.
Okay, yes.
You touch the button on the bottom.
Like this, okay. To follow up to the previous question, like these assumptions on the power of the attacker could be also in terms of dependence on the randomness, for example, on the weights of the model or on the part of the training set that the attacker doesn't have a power on. So I would want to understand if there is work in this direction, especially in the settings of high dimensional data where these dependencies might really improve the power of the attacker by so much.
Yeah, that's another interesting question. I mean, the work that I know, the two papers that I mentioned. So this is a very recent work. So it's called the review paper and this upcoming release paper. So it'd be awesome to see. I don't think there has been yet follow-up on this, but it'd be awesome to guys follow up on it.
Okay. Is that also what you commented about the continual learning? Because you were mentioning about verifying if the sample respects some sort of, well behavior. Because I would expect maybe in high dimension I can screw the the input sample in a way that I can destroy everything. But maybe I just cannot do it as an attacker because I do not see anything else other than maybe the input distribution or what I can actually do on the model.
Yeah.
Okay, this is not really a well-defined question. It's more about understanding what are reasonable assumptions in this settings or not.
Yeah, it's for me by reasonable assumptions. So, so I guess I would say the strength of this work so far is no matter what Attacker does, we characterize all the optimal vulnerabilities, right? And now you guys are saying that well, now let's also do the same analysis about the learner and make even more assumptions about what the data can do. And I totally think it's in direction. Yeah. And I guess, and then you can put various assumptions, down various assumptions what the data. I do think though that it's nice that you are able to characterize what the optimal learner, because sometimes I guess less assumptions of the attacker, potentially are positive, and get strong positive results. But given that our lower bound values are positive results, and there are distributions, as was mentioned, where the region that we can certify, there are distributions, the hypothesis rate of the region that we can certify could be potentially small in probability mass. But it does make sense to then try to look at analyze situations where we know more about the attacker, because maybe you can certify it more. But then you have a kind of procedure that you make a strong assumption that your assumption about the attacker is correct. Because if it's not correct, you go back to say you're not be able to certify something that is not correct at all. Yeah, but there has not yet basically been a subsequent talk on this point, so I'm very excited to see what will happen. It's so novel, so new stuff, not novel, so new, sorry. So recent, yes, right. So yeah, but we also need to follow up before we establish the dimension. Yeah.
So I'm interested. So in the slide where you discussed the efficient algorithm,
Yeah.
like reliable learner.
Yeah.
So you also mentioned like enumeration over hypothesis. So you essentially need to find the hypothesis with some smallest error rate. And I was interested, like, how important is it to enumerate over?
Now, this can be implemented efficiently. You mean this slide here? Actually, this step here can be implemented efficiently.
Yeah.
You just add many copies of the point X with a certain label, and you just run VRM on the resulting. So you just modify the training set by adding many copies of the point X with a certain label, and just run VRM. So this actually you can really do it efficiently.
Okay, even for like potentially nonlinear hypothesis spaces.
Assuming that I can do it efficiently, assuming that an ERM oracle.
Okay.
So an ERM oracle means, we want to put a point, find the classifier from your access space, because the smallest error rate, so we call it an ERM oracle. Yeah. If I have such an oracle, then I can implement this efficiently. Yeah.
Okay, thank you. Yeah.
But if I don't have it, then of course. Yeah.
Okay. Perfect. So join me in thanking Nina once again for the beautiful talk. So now we'll have just over half an hour of break. There is coffee and tea behind you, and we will reconvene at 11 for the second talk of the morning session. Thank you. Welcome back, everybody. Terrific. Welcome back from the break. It's wonderful to see everybody here in person, talking, having coffee. It's wonderful. So for the second talk of this morning's session, I'm very, very happy to introduce one of our very own, Professor Luana Ruiz, who's an assistant professor here at Johns Hopkins. Luana did her PhD at UPenn with Alejandro Ribeiro, and then she was a postdoc at MIT, as well as a Google research fellow at the Simons Institute for Computing. Luana, thank you so much for joining us here. Looking forward to your talk.
Thank you. Thank you so much for the invitation. Thank you all the organizers for the invitation. So today I'm going to be talking about some interesting results that we unveiled when we were studying large-scale graph machine learning. And specifically, in particular, I'm going to focus on 3 results related to these 3 keywords here. So I'm going to talk about trade-off with the discriminative power of these machine learning models on graphs that we unveiled when we were analyzing their convergence to large graph limits. I'm also going to be talking about some convergence guarantees for an algorithm that we proposed to essentially increase the performance of these machine learning models on large graphs. And then I'll also talk a little bit about the learning dynamics of graph neural networks or graph machine learning models on large-scale graphs by doing an analysis of the neural tangent kernel associated with these models. So as you all know, machine learning on large-scale graphs is important because the need to process information on large graphs arises in many, many important real-world applications. Right, so to give you 2 examples, here I have on the left, I have an example of a wireless network where I model the nodes of my graph model as transmitter-receiver pairs and the edges as interference between these communication links. And the idea here is that we want to allocate some power to each one of these transmitter-receiver pairs so that they're able to communicate. But there is the interference between these communication links actually prevents you from, having clean communications, right? So you have here an optimization problem, but at the same time that you're trying to say speak louder, right, to your receiver, you're trying to not generate too much noise in the channel as a whole. And so this defines an optimization problem on networks that are relatively large, especially when you think of like Internet of Things applications, right? On the right, I have another example where we're trying to do distributed control of teams of agents. So imagine that you have a team of robots or, for instance, drones, like on the image here that you want to control, and it's a large team. But controlling these in a centralized manner would be very expensive, right? Because it requires like a clairvoyant controller to control all of these agents at the same time. So control policy has to respect the essentially the sparsity pattern that is imposed by this communication graph, right? By this geometric communication graph in space. And so this is another example where we want to process the information contained in the agent states to be able to decide what is the next action, right? So both of these problems are examples of problems where machine learning has performed really well and is the solution of choice. And when I say machine learning, I actually mean graph neural networks, and graph neural networks because these are machine learning models where the parametrization is independent of the graph size, which is something that is desirable in these large-scale networks, right? But the issue with graph neural networks is that as much as they have shown good performance on graphs of small and moderate size, they are difficult to learn on large-scale graphs. And this is not too hard to see. In practice, these graph neural networks are not implemented using matrix vector multiplications, but at the end of the day, they are based on matrix vector multiplication. So it's not hard to convince yourself that as you increase the graph size, it will become more expensive to learn these models, right? At the same time, we have observed empirically that GNN scale. And what do I mean by that? What I mean by that is that we can train graph neural networks on a graph of smaller size. If we transfer it to our desired graph or target graph of larger size, we'll see that we make an error, right? but we still get relatively good performance. And so this is what I mean by them empirically scaling, right? But why do they scale? So a lot of my prior research has focused on trying to answer this question. And to answer this question, I have turned to graph limits, right? And why limits? Because limits reveal the intrinsic dimensionality of the data, which is typically smaller than the graph size. And this idea to look at limits is not new. I mean, it's borrowed from analysis of signal processing in Euclidean domains, where a small intrinsic dimension actually means that we have sampling and reconstruction guarantees, which in turn implies that convolutions, or in general linear shift invariant operators, converge from these discrete domains to continuous Euclidean domains, right? And this is precisely this property of convolutions in Euclidean domains is precisely what explains their success in a lot of image processing and computer vision applications. Now, what's good news is that graphs also have limits that effectively limit their dimensionality. There are many models for graph limits. One such limit, and the one that I'm going to focus on here, are graphons. But however, even though these limits exist, they do not have, there's still a challenge, right? Which is that they do not have the Euclidean structure that, for instance, time and image signals have in the limit. And so that complicates these analysis of sampling and convergence of convolutions, right? But what is nice is that their spectra converges, so it can be shown that their spectra converges, and graph convolutions and GNNs can be shown to be spectral operators. And so if you combine these two facts, you can show that graph convolutions and GNNs have well-defined limits on these graphon limits, which I'll define later, but which we call graphon convolutions and graphon neural networks. Okay, so this result, right, that graph convolutions and graph neural networks converge to graphon convolutions and graphon neural networks answers that question that I asked earlier, right? Why do GNNs scale well empirically? This kind of gives some theoretical support to that observation. But while I was doing my research, I noted that there's a lot of other questions that you can ask and that remained unanswered. For instance, does this convergence mean that we can practically leverage the success that GNNs have experienced in moderate size graphs and transfer it to large scale graphs, right? And if so, what is the trade-off? What is the price is there a price to pay, right? Second, say that I am interested in the extra error and convergence guarantees in the downstream task, right? What convergence tells me is that the outputs of these GNNs become closer and closer as I look further down in my convergence sequence of graphs. But how about the performance in the downstream task? Can I give any guarantees for that? And third, how does the graph size affect the learning dynamics of the GNN? And I think that's an interesting question to ask in situations where you can't really afford to train on smaller graphs. You have to train on your large target graph. So in this talk, I'm going to attempt to, present some results that I've worked on with others that attempt to answer these questions. So to answer the first question of whether we can leverage the success of GNNs on large scale graphs, we're going to see that the answer is yes, we can because GNNs are transferable from moderate size to large scale graphs with some essentially an upper bound on the error that we make when we do this transference. But this comes at the cost of discriminability in the spectral domain, so discriminative power in the spectral domain. And I'll be more clear about this point in a few minutes. To answer the second question of whether we can have error convergence guarantees in the downstream task, I'm going to tell you about an algorithm that we worked on, which essentially is very simple. It just proposes training your model not on a single small graph, but on a sequence of growing graphs. And then we show that GNNs trained on these convergent graph sequences converge to the optimal limit graphon neural network in the sense that the optimal here is the graphon neural network with weights that minimize the empirical risk minimization problem on the limit graphon. And then finally, I'm going to talk a little bit about the learning dynamics of GNNs on large-scale graphs by defining graphon neurotangent kernels and showing that graph neurotangent kernels converge to graphon neurotangent kernels on the limit graphon. So let's get started. So before I start, let me kind of give you some basic definitions on graphs, graph convolutions, and graph neural networks. So I'm going to represent graphs here as by their adjacency matrix that I write S here. So this is an n by n matrix, and graph signals, so data on top of the nodes of a graph, as vectors x in Rn. And so with the setup, we define a graph convolution as this weighted polynomials of the adjacency matrix applied to graph signals, right? And the reason why this figure is here is because, you can interpret every element of this polynomial as essentially doing a k-hop shift of the information on the nodes of the graph, and then aggregating, linearly combining these k-hop shifts using these weights h, which we'll see, you could either design if you just have a typical signal processing application, or that you can learn if you're in a learning setup. Now, an interesting result about these graph convolutions or graph filters is that they can also be represented in the spectral or frequency domain of these graphs, right? So this is the node domain representation. When I say spectral domain representation, I'm actually referring to the representation on the eigenbasis of the adjacency matrix of the graph, or the eigenbasis of the graph. So, I'm focusing on symmetric graphs, so the adjacency is always symmetric, and so it always admits an eigendecomposition. And then to look at the frequency or spectral representation of these graph convolution, I define a graph Fourier transform, which is just the projection of my input signals x and output signals y onto the eigenvectors of the graph. And then what this theorem is saying here is that the graph Fourier transforms of the input signal and the output signal are related by the spectral representation of my convolution, which is just a polynomial with weights hk, right? So same as before, on the eigenvalues of the graph, right? And this result is very simple, but it's still interesting because it's telling us two things. It's telling us that the operator is pointwise in the spectral domain, meaning that the jth spectral component of my output signal is related to the jth spectral component of my input signal by a polynomial that only depends on the jth eigenvalue, right? And it also allows me to decouple the filter from the graph because I can represent the spectral response in terms of an arbitrary scalar variable lambda, right? And so what would change here if I transfer this convolution to another graph is just the graph eigenvalues, and I can readily evaluate the spectral response of this filter in other graphs. So given a graph convolution, these graph convolutional neural networks that I'm interested in here are very simple kind of architectural modifications of graph convolutions. They consist of a sequence of layers where each layer is itself a graph convolution composed with a pointwise nonlinearity, which acts node-wise on the nodes of the graph. And so like graph convolutions, graph neural networks inherit this property from graph convolutions, and they're also spectral operators, right? And in future slides, I'm going to refer to graph neural networks as this map phi parametric on the convolution weights h at all layers, on the graph matrix, and on the input nodes, the input graph signal. Okay, so that's it for graphs and graph convolutions and graph neural networks. Now let me talk about graphons and define the counterparts of these objects on graphons, right? So the definition of a graphon is as a bounded symmetric measurable function mapping points from the unit square to the unit interval. And the easiest way to think of a graphon is as a weighted symmetric graph with an uncountable number of nodes, where you should see the labels as the nodes, right? So the graphon arguments u as the nodes, and the edge weights, or the probability of sampling an edge, are the graphon values WV, evaluated at the labels of nodes UV. Now here, we're more interested in two theoretical interpretations of graphons. The first one is as the limit of a sequence of graphs, in the sense that the densities of certain graph motifs on these convergent sequences of graphs converge to the probability of sampling those same motifs from the limit graphon. And then a second interpretation, which is almost like the duo of that interpretation, which is an interpretation as a generative model for graph families that we generate by sampling edges ui, uj, Bernoulli with probability w, ui, uj. And just to give you an illustration of these two interpretations, so we can see the limit interpretation by going from left to right here on the slide, right? So in the right, I have a stochastic block model graphon with two communities. And I can see by looking at this that structurally these stochastic block model graphs with increasing number of nodes are converging to that graphon. And in fact, you know, like going back to the generative model or sampling interpretation, I generated these all of these graphs by sampling them from the graphon. So sampling the nodes uniformly at random from the 0-1 interval, and then sampling the edges according to W. Okay, so in the same way that we define the graph convolution as a polynomial in the adjacency matrix of the graph, here we define graphon signals x, which are now functions from 0-1 to the reals. I focus on functions in L2, so finite energy signals, if you will. And we define TW, the integral linear operator with kernel given by W, right? So that's the analogous of my graph shift. This is my graphon shift. And then with these two definitions in hand, we define graphon convolutions as these polynomials on these operators TW, right? So each TWK corresponds to a k-hop information diffusion on your graph, and the convolution is just this linear combination of these diffusions with weights hk. Now, analogously to graph convolutions, graphon convolutions can also be represented in the spectral domain of graphons. The reason for this is because the graphon operator is a self-adjoint Hilbert-Schmidt operator, so it has this real spectrum that is not finite, but it's countable. And so we can again define graphon Fourier transforms, which are projections of our graphon signals onto the eigenfunctions of the graphon operator. And we can relate the graphon Fourier transforms of my input signal and my output signal, again, by a polynomial that only depends on the weights hk and on the eigenvalues of my graphon, right? And so if you go back and contrast this with the same slide that I had for graph convolutions, these are the same expressions, right? So like graph filters, graphon filters also have pointwise spectral response and are decoupled from the underlying graphon. And at this point, I'm probably boring you, but you know, same as graph neural networks that were these sequences of layers with graph convolutions and pointwise nonlinearities. For graphon neural networks, this is the same, right? So graphon neural networks are compositions of layers where each layer is consists of a graphon convolution and a pointwise nonlinearity. And again, we are going to parametrize or represent graphon neural networks as this map phi, with the only difference that now this is a parametric map on the graphon and not on the adjacency matrix, right? And from here, it's not difficult to see that this is essentially the same algebraic object as the GNN, right? But parametric on the graphon. Okay, so before I get to the novel results that I want to talk about, let me talk a little bit about graph neural network convergence, which I mentioned follows from the fact that these are spectral operators earlier, right? So to understand why GNNs converge, we have to look at the spectrum of graphs and their limit graphon, right? So an important result due to Borgs and Chase and others is that in a convergent graph sequence converging to a graphon, the eigenvalues of the graph that I'm representing here as these kind of blue directs, they converge to the eigenvalues of the graphon that I'm representing in red here, right? So this is just a toy kind of visualization. And so, you know, since I showed you that the spectral response or frequency response of graph convolutions and graphon convolutions is essentially the same if the weights hk are the same, from this convergence of spectra, it's not surprising that graph convolutions and GNNs converge to graph-on convolutions and graph-on NNs, right? But what does that mean in practice, right? Can we use this results in practice, and are there any trade-offs? So to understand that, we took that this convergence analysis, which I don't have here, but that we did, and which was an asymptotic convergence analysis, and we attempted to derive a non-asymptotic bound for this convergence of graph neural networks to graph-on neural networks, and this is the bound that we have here on the slide. So what this theorem here is saying is essentially, if I have a sequence of if I have two graph signals that are sampled from the same graph-on and graph-on signal respectively, and I consider the outputs of a GNN with same weights h on both of these graphs, then the norm difference of the respective graph-on induced signals, so the representation of these graph signals on the limit graph-on, is upper bounded by a term that decreases with the size of both graphs, which is expected as we have asymptotic convergence, right? And so what this is essentially giving us is a transferability error bound, right? What do I mean by transferability? This means that we could train the GNN on one of these graphs, and we could transfer it to the other graph. We could transfer its weights to another graph with an error that is upper bounded by this expression here, and which decreases with the size of both graphs, right? So before I talk a little bit about other terms in this bound, let me show you an example of how this transferability of GNNs is useful in practice. So going back to that wireless resource allocation example that I gave in the beginning of the talk, imagine that we want to train a resource allocation policy using a GNN on a smaller graph with 50 transmitter-receiver pairs, and then we want to transfer it to larger graphs, right? So with more transmitter-receiver pairs here in the x-axis. So what we see is that when we apply this GNN trained on the small graph to these larger graphs, we still get pretty good sum rate, which is essentially the utility measured metric that we're using here. And we get better utility than the utility of other heuristics that are typically used to do resource allocation in these networks with a gap in performance that actually increases with the graph size, right? So this is a practical example of how this can be useful. Now going back to the bound, so let me just go back a few slides. So something that I hid here, or that I went over quickly, was this dependence on all these other terms. I'm not going to cover the dependence on these terms in gray, but an important dependence here is on this term AH. And this term AH is the Lipschitz constant of the frequency response of my convolutions in the spectral domain. And so what you can see from this bound is that when this Lipschitz constant increases, the upper bound increases, right? Implying that the transferability error upper bound becomes worse for filters with higher Lipschitz constant. And so this alludes to a trade-off between transferability and spectral discriminability, right? Because if I want my filter to vary a lot in the spectral domain, it will have a high Lipschitz constant, and therefore it will have a larger transferability error. In order to have a smaller transferability error, I actually need my filters to be a little bit flatter, right? And I'm not going to go into the details of why this filter doesn't have to be flat everywhere here, but I'm going to give you some intuition for why this is the case. And the reason for that is because, as you can see, even though the spectrum of graphs converges to the spectrum of graphons, this spectrum is contained in the -1 interval, and so it accumulates near zero. Zero is the only accumulation point, right? And so in the end, I mean, what this accumulation means is that the convergence of the eigenvalues is not uniform. And because the convergence of the eigenvectors, which we need to take this result back to the node domain, is not uniform either. And so when we have a filter that varies a lot here near zero, we incur, like we have a high risk of incurring in eigenvalue mismatch here. So essentially we might be amplifying two spectral components associated with different eigenvalue indices very differently, and we don't want that. So that is what causes the increase in the transferability error. And so this is where that trade-off between transferability and the discriminative power in the spectral domain comes from. Now, the way we kind of address it is we impose like a constraint on our filters, right? So we say, okay, for eigenvalues between minus C and C, where C is a constant that we fix, we need our filters to have limited Lipschitz constant, bounded Lipschitz constant. And to give you an example of how this trade-off shows up in practice, here I have an example of, it's a movie recommendation example. So here what I did is I have a network where the nodes correspond to movies and the edges correspond to similarities between these movies. And I have signals which are ratings that a user has given to some of these movies, not all of them. So there are some missing ratings here. And I want to train a graph neural network that, given this graph and given this signal with missing entries, will interpolate that signal and give me the missing ratings for product recommendations or movie recommendations down the line. And so here on the right, I'm plotting the difference between the MSE that I get on my training graph, which has size given by the values here in the x-axis, and the MSE achieved by the same network that I trained on these small graphs on a target graph with 4,000 movies. And so we see that the difference between the MSE increases as we increase the training graph size, which is expected from convergence and transferability. But we also see the trade-off here because here I'm comparing, so a GNN that I train unconstrained in orange, and a GNN that I train by penalizing its Lipschitz constants. And we see that the transferability error of this Lipschitz GNN, as I'm calling it, is always smaller for any training graph size than the transferability error of the GNN trained unconstrained. So this is like empirical evidence of this trade-off in practice, right? Okay, so that was it for the trade-off. Now let's move on to the second question that I asked, which was whether we can have error or convergence guarantees in the downstream task, right? And the reason why we asked ourselves this question was because, okay, we can train GNNs on small graphs transferred to large graphs by using the transferability property, but in some applications, this might not be sufficient, right? It could be that the error that you make is too large, and it could be that in your application the error allowance is small. Think, for instance, of these multi-robot systems and defense applications and hazardous environments and things like that. And so the minimum training graph size that is given by that transferability upper bound might still be too large, and then we haven't solved our problem. We still have to train on the large graph. And so in this case, what we proposed to do was to leverage this convergence or transferability of graph sequences in the training of algorithm of the graph neural network itself. So we proposed this learning by transference algorithm here for empirical risk minimization, which does the following. So here we were resampling graphs every epoch, but you could do this every few training steps. You could change this. But what we do is, at each epoch, we increase the number of nodes. Then we sample a new graph, a new larger graph from our limit graph one or our limit graph. And then given this graph size, then we obtain a sample from our distribution, right? We construct the graph sample, and then we take a gradient step on this graph of size NE. And then in the next epoch, we would have increased the graph size, increased the graph, right? And we would be taking a gradient step on the larger graph. And we do this iteratively, right? So what we were able to show for this algorithm was that when we train a graph neural network in this way, so in a sequence of graphs, we are able to, in a finite number of training steps, obtain a graph neural network that converges to an epsilon ball of the solution of the empirical risk minimization problem on the limit graphon. And this doesn't happen, always. You have to respect a condition, an assumption, and this assumption is that at each training step, you have to make sure that the norm difference between your gradient step on your current graph and the gradient step that you would be taking on the limit graphon is less than the norm of the gradient step on the graphon itself. Okay? So essentially, you need the error that you make in the gradient computation to be less than the norm of the gradient itself. And then provided that this is satisfied, then you have convergence of this algorithm to the optimal graphon neural network in infinite number of training steps. We haven't derived actual rates for this, but it's an interesting future direction for future work. And then let me just see how I'm doing on time. Okay. And then just to show you how this algorithm is useful in practice. So we tested it on that flocking or multi-agent control example that I gave you in the beginning of the talk, where the goal here is to train a GNN-based controller that is leading these agents that are initialized kind of at random on the plane to flock, right? So to fly it with the same speed in the same direction and maintaining a formation, like this organized formation. And so what we're optimizing for here is the control cost. So here I'm plotting the control cost of GNNs that are trained directly on the large graph, which had 100 agents here. So these are these flat lines. They are different because one is trained for less epochs than the other. And then these curves, these curves that decrease are the control cost achieved by my GNN trained via the learning by transference algorithm at each epoch, right? So it starts out very high, but at every epoch, as I increase my graph size and I keep learning, it decreases up to the point that with about half the number of epochs that it took to train the GNN on the limit graph, we achieve more or less the same control cost. And what we gain here is, we achieve the same performance, but what we gain is in terms of computational time or computational complexity, right? Because if you look at this plot here on the right, the time that we spend per epoch, depending on the number of nodes of the graph that we're training on, increases steadily with the graph size, right? So we didn't compute the actual time. Well, actually, I have some. I know I don't have the time here, but you could compute the time that it takes to train by the learning by transference algorithm and contrast that with the time that it takes to train on the large graph by adding up these times per epoch here. Okay, so now let's move on to the third question that I asked earlier, which is how does the graph size affect the learning dynamics of the GNN, right? So in order to analyze the learning dynamics of the GNN, we used the neural tangent kernel analysis, which is this analysis for the learning dynamics of neural networks in this wide overparameterized regime. So it's an analysis that is only valid when you make the width of your neural network tend to infinity. And the way this analysis goes is if you compute kind of like the gradient flow of your neural network, you see that the gradient descent dynamics of your neural network under least squares regression is described by a kernel theta here, defined by this expression here. And what a nice paper by Jacot and others showed is that this kernel, which they call the neurotangent kernel, converges to a kernel that remains unchanged during training as you make the width of your neural network tend to infinity. Actually, that is the neurotangent kernel. So this limit kernel is the neurotangent kernel, right? So the kernel theta in infinite width converges to this neurotangent kernel. And so in this limit, what happens is that you can show that neural network training becomes equivalent to doing kernel regression with this neurotangent kernel, which defines this feature map. So this, there's this equivalence between neural network training and doing kernel regression using this feature map. And as a result, because of this equivalence, what this means is that the principal eigendirections of the neurotangent kernel will correspond to the directions of fastest learning of the neural network. So this is how the neurotangent kernel can tell you a little bit about the learning dynamics of these neural networks in this infinite width regime. Now, before I go further and talk about how this applies to GNNs, I just want to clarify here that the width of the GNN is the number of features per layer. So before, when I was talking about graph convolutions, I was just considering one feature per layer. In this case here, so we have this left matrix multiplication with the adjacency matrix of the signal X here, which has components in n nodes, but now also has components in D features. So this is an n by D matrix now. And H here is the matrix that transforms these D features into, F features in the next layer. And so when we say that we are in the regime where the overparameterized regime would mean the regime where D is tending to infinity here. Okay, so actually let me tell you something else. So this analysis of neurotangent kernels, it has also been extended before being extended to GNNs by other people. It was also extended to convolutional neural networks. And what you see when you do this analysis in these convolutional neural networks is that in the node dimension is akin to a channel dimension. Okay, and so all of those properties of the NTK, right? That it's in the limit, training the neural network is equivalent to doing kernel ridge regression with the NTK, and also that you can use the NTK to analyze the learning dynamics of your neural network. Those properties carry through to convolutional neural networks because with the CNN you're just adding a channel dimension. So what we did is we computed the graph neurotangent kernel and the graph-on neurotangent kernel associated with our graph and graph-on neural networks. These expressions are a little ugly, but they're very simple to compute, right? You're just taking gradients with respect to the weights. I'm not going to parse this, but if you analyze these closely, unexpectedly, these are the same algebraic object. The only thing that changes is one depends on the graph, the other depends on the graph-on. So before I talk about the convergence result from GNTKs to graph-on NTKs, we wanted to do a sanity check to see if indeed we observe this alignment between the GNTK and the GNN as the width increases. So what we did was, we considered an opinion dynamics problem where you're trying to use a GNN to predict opinions given an initial opinion. Simplistically, you can think of this as like a consensus problem that we're trying to approximate with the GNN. And we can't really plot graph signals, right? Since they're n-dimensional, we can't really plot the output graph signal with respect to the input graph signal. So what we did here is we're plotting just one spectral component of the output signal versus the same spectral component of the input signal. And what we see here is that as we increase the width, first of all, what happens is that the variance in these outputs of the GNN and GNTK decreases for different weight initializations as we increase the width of the GNN. And we also see that as the width increases, this GNN and GNTK curves align. So we're kind of seeing this behavior that, training the GNN is becoming similar to doing regression with the NTK or with that kernel as the width increases. And granted, this is just for the second spectral component, but it's nice to see this sort of behavior. Okay, so with that sanity check done, then we went on to analyze the convergence of graph neural tangent kernels to graphon neural tangent kernels. Here we were considering the case where you have GNNs with a fixed number of layers, a fixed number of diffusions, so that parameter K was fixed per layer. And since the GNTK and the graphon NTK are the same algebraic object, it's not too hard to show that if the graphs are converging to a limit graphon, the GNTK should converge to the graphon NTK in this appropriate operator norm. And so what this result tells us is that even though we don't have an asymptotic bound as before, is that we could fit the graph neural tangent kernel on a smaller graph and then transfer the kernel regression weights to make predictions on the larger graph, right? And so to visualize that empirically, we did just that on two numerical examples. So the first one was in the opinion dynamics problem that I mentioned earlier. We see that as we increase the graph size, the relative MSE difference between the neural tangent kernel on the graph on which it was fitted, the small graph, and on the large graph decreases. And similarly, we conducted the same experiment on citation networks, where the nodes are papers, edges are citations, and you're trying to predict the community, the scientific community of each paper. And we also observed the sort of decaying behavior of the error difference as the network size increased. Now, this convergence of these graph neural tangent kernels, it's interesting, but it still doesn't tell us about the learning dynamics of GNNs and how it converges on large graphs, right? Because that information is actually contained in the spectrum of these neural tangent kernels. So we also did a spectral analysis of these neural tangent kernels on the graph and on the graphon, and you're able to show that the eigenvalues of graph neural tangent kernels in a convergent graph sequence converge to the eigenvalues of the graphon neural tangent kernel, and the eigenspaces also converge in the sense that the projectors associated with those eigenspaces converge. And so this is nice because it tells us that the speed of convergence of the GNN along each eigendirection of the GNTK is given by the corresponding eigenvalue, right? And so we can use the eigenvalues of GNTKs fitted in smaller graphs to estimate the speed of convergence of large graph GNNs along those eigendirections. And so this gives us a little bit more insight into what's happening when we're training GNNs on these large graphs without actually needing to analyze the GNTK on the large graph. And so here, this is my final numerical example. What we did to try to visualize that result empirically was we fitted graph neural tangent kernels on the citation networks for graphs of increasing size. And then we plotted the first eigenvalue here on this log axis. And so we can see that as we increase the graph size, right, we go from 400 to 2000, the eigenvalues of these graph neural tangent kernels seem to converge. So to conclude, I just want to summarize the things that I talked about. So, we talked about how GNNs scale well in practice because they converge to graphon neural networks, right? This convergence is not unexpected because these are spectral operators and the spectra of graphs converges to the spectra of graphons. But it also unveils important results. So the first one is that, convergence actually means transferability. We can train on moderate-sized graphs, transfer to larger graphs. And it also reveals a trade-off between this transferability and the discriminative power in the spectral domain. And then we also saw different ways in which we can extend this, right? We saw that we can do better by leveraging graph convergence in the gradient descent convergence by proposing this new learning by transference algorithm. And we also used this graphon analysis to understand the limit behavior of GNN learning dynamics on large graphs. Before I conclude, I just want to do some advertising of Thene's talk tomorrow. So, there's a lot of future research directions that we can explore. So in all of the results that I was talking about here, we only consider random node sampling. We're not sampling trying to preserve spectra or spectral content of signals or anything like that. And so even though it's a little bit harder to do that than in like Euclidean domains where you can just like respect the Nyquist rate, this is an important question. And so Thene and I have been working on the sampling theory for graphon signals, so I invite you to come. And then there are other ways you can extend this. I mean, graphons are by no means the only graph limit. It actually has limitations. It's only a good limit for dense graphs. And so we've been looking into exploring manifold limits for geometric graphs, LP graphons, which are these graphons that have a more tunable sparsity, other convergence paradigms that cover from bounded degree graphs to bounded average degree graphs, as well as dense graphs, and other GNN architectures beyond convolutional. So that's all I had for today. Thank you very much.
Thank you so much, Luana. We'll take some questions. Also, for the people asking questions, try to use the microphone so that people on the live feed can also hear you. So are there any questions for the speaker? Yes.
So do we have any framework to talk about generalization error in this setting? Because you're talking about the operator approximation, training dynamics, or training error. What about generalization error?
That's a great question. So I haven't worked on that myself, but so here Masquet, Ron Levy, Gita Kutinyok, they have a paper on that where they analyze generalization error for sequences of graphs converging to a graphon. I don't remember if it's a graphon or a more general graph limit, but that has been studied.
Yes. Maybe while I walk there, I'm going to ask a question. So in the first part of transferability for graphs of different sizes, so basically this, if I understood this correctly, this works because all of these are approximating the same graphon, but they provide different errors, and then you can quantify those errors based on the different sizes of the graphs. So this should also work if they are approximating slightly different graphons. Mm-hmm. Is that right? And if so, can you now make a claim about not just generalizing across different sizes of graphs, but also to different distributions of graphs?
Mm-hmm. Yeah, that's a great question. So that would be a question of stability, right?
Yes.
Essentially, you could see this other similar graphon as a perturbation of your original graphon.
Correct.
And look at the stability of these graph neural networks to these small perturbations. The complicated thing here is that the spectrum is contained in that -1 interval, so perturbations can be very bad for those small eigenvalues, right, that are accumulating.
Right, nice talk. So I was wondering if you have looked at feature learning infinite width limits in graph neural networks, which don't converge to a static neural tangent kernel.
Is the questions about feature learning?
Feature learning infinite width limits of neural networks.
I haven't looked into that. No. Do you mean something like unsupervised learning, kind of learning these embeddings of these graphs?
No, I mean there are specific infinite width limits which don't result in static neural tangent kernel. Rather, they result in neural tangent kernel that evolve as a function of time.
Yeah, that's an interesting question, but no, I haven't looked into that.
Thank you. So I understand that the spectrum of the neural graph neural tangent kernel has something to do with generalization. How should I think about the spectrum of the adjacency matrix? Is that a completely different thing, unrelated, or is there some link between these two things, or?
So I don't want to say there's no relationship between these two things, but they are different in the sense that the spectrum of the graph essentially tells us which signals, I guess, could be well represented by a model running on these graphs, right? Okay. Now, the spectrum of the GNTK, I guess, is unrelated in that sense, but I believe there's a connection, right, between those two. I think one will depend on the other, but I don't know in what is this connection, but it's definitely an interesting question.
Okay.
Yeah, thank you for the interesting talk. I'm wondering, because I know graphons are limits of dense graphs. So I wonder how would the result change if you consider sparse graphs, because real graphs are ultimately sparse.
Mm-hmm. Yeah, so you notice that our analysis here is carried out in the spectral domain, right? So it depends on convergence of spectra. What happens when you start looking at sparser graphs is that you don't have convergence of spectra anymore. So in manifolds for graphs, geometric graphs that you stem from manifolds that are still dense, but less dense than these graphs converging to graphons, you still have convergence of spectra. So you can do that same type of analysis there. But when you have, for instance, bounded degree graphs, you don't have convergence of spectra anymore. I know Thien was looking into this at one point, but it looks pretty hairy. So the analysis would have to be completely different.
I see. Thank you.
Okay, join me if there are no more questions in thanking Luana once again. And now we go on to the lunch break. Lunch will be provided in the room immediately sort of adjacent to this glass pavilion, and we will reconvene at 1:30 for the next plenary talk.
Please be seated, and we're going to start our afternoon session soon. Okay, welcome back to our afternoon session for the DeepMath conference. It's my great pleasure to introduce Aaron. Aaron is the Henry Salvatore Professor of Computer and Cognitive Science from the Department of Computer Science of the University of Pennsylvania. He also holds secondary appointment in Department of Statistics and Data Science at the Wharton School. His main research interests are in algorithms and machine learning, especially in the areas of private data analysis, fairness and machine learning, game theory, and mechanism design and learning theory. I'm a big fan of his book, The Ethical Algorithm, which I read a lot in my postdoc years. So it's my great pleasure to introduce you, and very excited you're here. The floor is yours, Aaron. Thank you.
Me. And I'm going to talk about a line of work I've been working on for a little while with a bunch of great colleagues, faculty colleagues, Osbert and Ricky, and students, and former faculty colleague Malesh, and students Varun, Chris, George, and Ramya. Let's see what I need to click on to make this work. Okay, and and it was like the deep math, and so I wasn't sure whether I was supposed to speak about like deep mathematics or like math related to deep learning, and so I decided to just split the difference and do neither of those things. But I did ask Dolly to make a title slide for deep math, so there's the deep learning. Okay, but here we are. We're in what, 2023. We've got all of these technologies that are in various ways extremely good at making predictions. Okay, meaning when we measure things like average error, often the average error is small. We're good at making predictions. But of course, the predictive technologies are not perfect. Sometimes they make mistakes. And to the extent that we want to use these predictions to take downstream actions that have consequences, it would be good if we could know on which particular predictions we have confidence and on which particular predictions we think we're more likely to be making a mistake. And so there's various ways you can quantify uncertainty. We'd like to quantify uncertainty. The main one I'm going to focus on in this talk, I'll touch on a few at the other ways at the end, but the main one I'm going to focus on in this talk is prediction sets. So rather than making a point prediction, rather than saying, this critter over here is like definitely a marmot. Instead, I will produce a set of predictions. The goal would be to make just a single prediction, but if I have uncertainty, I might want to predict a set so as to specify where that uncertainty lies. Okay, so instead of saying this critter is a marmot, I could say, well, I think this critter is either a marmot or a fox squirrel or a mink, etc. Right? The size of the prediction set is telling me something about the degree of uncertainty, but more than that, the contents of the prediction set is telling me about where the uncertainty lies. And it might be for the decision I need to make downstream, the uncertainty doesn't matter. I might, if I'm driving my car, I might only care that the thing in front of me is a critter, and whether or not is a marmot or a fox squirrel, the right downstream action to take would be to apply the brakes. Okay. We can do it for regression problems too. Then a prediction set is a more familiar object, like a prediction interval. Now these prediction sets, they should mean something, right? And so like the goal is that they should have some coverage probability. The prediction set should cover the true label with probability 95%. And what is that probability taken over? Well, that's something we're going to interrogate in this talk. Okay. So let me give you, like a one-slide crash course in conformal prediction. If you stop listening after this slide, you will still have learned something interesting. At least if you didn't know what conformal prediction was before. And it is an extremely simple, its main merit is simplicity, method for affixing a prediction set that have some semantics to arbitrary black box models. Okay, so here's how it works. You start with your favorite model. Okay. I'm going to, just for the sake of simplicity, assume it's a regression model, but it could be a classification model as well. And I don't assume anything about it. To me, it's a black box. It maps features to labels, to predicted labels. Okay, so if it's a regression model, it maps features to like numbers, f of x. And then I pick what I'm going to call a non-conformity score, which could again be anything. We're going to make no assumptions at all about this score. It's just some function mapping feature label pairs to real numbers. But what you should think of this as telling you is how different the candidate label y is from the prediction made by your model, or how surprised you would be if you saw label y given features x given what your model predicts. And so again, we're not going to make any assumptions about the function, but a very natural one to keep in mind in a regression problem is that the given features x, the non-conformity value, the surprise value for some label y hat is just the absolute value difference between my prediction, f of x, and y hat. The more different the label is compared to my prediction, the bigger this value. And then I'll take some holdout set. I'll take some data that hopefully is, draw an IID from the same distribution I'm going to test my model on, consisting of labeled examples. And what I'm going to do is I'm going to, for each labeled example, compute the nonconformity score. Okay, it's going to give me like a number for each of these examples. And I'm going to compute a 95th percentile quantile of this score distribution, a threshold such that for 95% of the examples, the nonconformity score is below this threshold. And on a new example, I'm going to produce a prediction set. What's it going to be? Well, on the new example, I see x, not y. My prediction set will consist of all labels y whose nonconformity score when paired with x is below this threshold, is below this 95th percentile quantile. Okay? In our simple example, this is just an interval centered at our prediction that has width equal to this threshold, but in general, this is a well-defined object for any pairing of model. It could be a classification model and nonconformity score. And once you've seen this, you could work out, on a napkin, it's very simple at this point, that if you do this without, so long as the data was sampled IID, then with 95% probability, on a new example, the label will be contained within the prediction set you produced. Okay, 95% over what? Well, over everything. The probability here is over the randomness of x, it's over the randomness of y, it's over even the randomness of the calibration set. Okay, so that's what I'm going to mean by a marginal guarantee. So that's great, but why might we want more than marginal guarantees? Well, let's interrogate that question with a cartoon. Suppose a patient comes into the hospital and the doctor tries to predict something relevant to the patient's care. Maybe the doctor says, well, given your features X, given what's in your medical record, what I observe about you, I've got this model. It predicts your blood oxygen level in 24 hours time is going to be something, f of x. Maybe we're going to make a decision as a function of this. Are we going to admit you to the ER or not? And since this is, like maybe an important decision for the patient could ask, well, how sure are you of this prediction? And having listened to the talk up until this point, the doctor might say, well, I've got a 95% prediction interval that your blood oxygen level will be within some interval, L of x and U of x, and maybe I would make the same decision for every point in this interval, and so I therefore feel confident in making the decision. And our patient thinks to herself, So, like, what do these probabilities mean? From the point of view of a decision maker, from the point of view of the patient who is hoping to, solve some, like decision problem, figure out whether it is in fact in her interest to, be admitted to this hospital or not, or, get a second opinion. Our patient is kind of hoping that this probabilistic statement is about her as an individual, or at least conditions on everything that is known about her, right? Like, that the prediction is about her to the extent that that is possible. She's hoping a statement about the conditional probability of y given x, where x is her features. But that is not what this is promising. Okay, if it's a rich feature space, if we've never seen anyone exactly like this patient before, if you think about it for a moment, you realize it would be impossible to promise something like this. What conformal prediction and many other methods promise are marginal guarantees, which, syntactically it looks kind of similar, but semantically it's quite different, right? Because a marginal guarantee takes the randomness over X as well, which means it is averaging over patients. All it is saying is that for 95% of patients for whom we make predictions, we cover the label. It says nothing about this patient. And so, right, our doctor has given this 95% prediction interval. Our patient could think thoughts like, well, I'm part of a demographic group, maybe a medically relevant demographic group that is kind of small, that represents less than 5% of the population. Consistent with the guarantees of a marginal prediction interval might be that the model has just entirely failed to learn about this relevant demographic group and, like undercovers on this group, and that's made up for by overcovering elsewhere. It could cover the label for people in this group 0% of the time. That would be consistent with marginal prediction. Okay, now, if we thought the medically relevant groups were disjoint, we could just separately run this procedure for each of those groups. But, like they're not always disjoint. So, our patient, she asks the doctor, what about for people like me? Well, what's the doctor going to say? What does it mean to be like this patient? The doctor could say, well, for African Americans under the age of 50, the 95% prediction interval is from A to B. And for women with a family history of diabetes, the 95% prediction interval is from C to D. And for people with egg allergies and no history of smoking, the 95% prediction interval is from E to F. And our patient might be a member of all of these groups. These might be very different prediction intervals, consistent, again, with the guarantees of marginal prediction. It could be that A to B is an entirely disjoint interval from E to F. These things don't even need to intersect. Okay, and so what should our patient do with this? Not clear. This is one of the problems I want to address. Okay, let me complain about one more thing before I start proposing solutions. The standard assumption in conformal prediction is that the data is drawn IID from some distribution or is at least exchangeable, meaning you could permute it without changing the distribution. Okay, so it's an assumption that says the future must look like the past, which is a very useful assumption, but not something that's always true. Okay, so I probably don't need to convince you that this is not always true, so let me just show you like a cartoon instead and then ruin it for you by telling you the punchline. Right, so here we've got like, I don't know, like a cool looking teenager. And he's just made it to the front of what was probably a pretty long line to see Santa Claus, to ask him about, his Christmas gifts. And Santa stops him before this cool dude can tell Santa what he wants. He says, don't worry, you don't even need to tell me, because this year we've pre-made your gifts based on a machine learning model. We have your requests for every year previously. You've been on this world for like 18 years now. We've trained a machine learning model, very minimal assumptions, just exchangeability, and we're predicting what you want. And this kid, he looks disappointed, and the punchline is that the sequence of your Christmas wish, your Christmas wishes is not an exchangeable sequence. Okay, that's the joke. Okay, so our goal is to mitigate these problems I'm actually gonna, walk you through a series of results. Okay, so we want to make stronger than marginal guarantees in various ways. The first set of results I'm going to walk you through is going to make stronger than marginal guarantees, but it's still going to assume the data is drawn from an IID or exchangeable distribution. Then we're going to want these stronger guarantees, but also not assume anything about the data. Yes?
Yes, so I understand there's X and Y. So where does the region pass?
There's today's X and tomorrow's X. We haven't written down a model yet, but you can at the moment use your natural understanding of concepts like future and past. Okay, so the second set of results, we want to assume nothing about the data. This is the set of results where time will become relevant. It'll be a sequential model. And then, conformal prediction ultimately is about quantile estimation. It's about estimating quantiles of nonconformity scores. I'll talk a little bit about uncertainty quantification beyond quantiles, right? You might be interested in variances, conditional value at risk. There's stuff out there beyond quantiles. Okay, so what's going on in conformal prediction? Well, fixing the point of a non-conformity score is to reduce this high dimensional problem of coming up with a prediction set to like a one-dimensional quantile estimation problem, just to estimate quantiles of this single-dimensional score distribution. And so the prediction sets are parameterized by quantiles of this score distribution. In the simple split conformal prediction world I told you about, you just pick a threshold, and for every threshold there is a prediction set. And the nice thing about this is it lets you abstract away the details of the prediction model and the nonconformity score. It just sort of reduces the problem to predicting real valued intervals between 0 and tau. Okay, so split conformal prediction, it's a wrapper that lets you take as input any model, any nonconformity score. We're going to try to design the same kind of object. So from now on, I'm going to think about predicting quantiles of an arbitrary nonconformity score. Whatever your favorite score is that you use for your favorite conformal prediction method, you can use it here too. Okay. Now, we're going to ask for prediction sets that satisfy stronger guarantees, stronger than marginal coverage. So we're not going to define our prediction sets by a single threshold anymore, but rather by a model that maps features to thresholds. Okay, so the predictions, there'll be a function f that maps examples to thresholds. The prediction sets we're talking about are going to be the set of all labels such that the nonconformity score, when evaluated at that label, is less than the threshold predicted by f of x. Okay, and now let me tell you about the ways in which I want to strengthen conditional coverage. The first is going to be a group conditional validity or group conditional coverage. So suppose I've got a way of partitioning, or not partitioning, of dividing examples into different groups. They can intersect. Okay, so for example, think about all of the demographic groups that came up in our conversation with the doctor. Those would be, examples of groups. Or more abstractly, suppose I've got, objects that have a shape and a color and a luminosity. Okay, so I've got triangles, I've got circles, I've got squares, but I've also got blue objects and green objects and orange objects. I've got glowing objects and non-glowing objects. These are different ways of dividing up the objects, and they intersect. You have a color, a luminosity, and a shape. Okay, so now fix a collection of groups. What group conditional coverage asks for is just that I should cover 95% of the labels, not just marginally, not just overall, but conditionally on membership in each of these groups, even though they intersect. Okay, so just going back to our little cartoon with the doctor and the patient, rather than giving 3 prediction intervals to this patient, we should give 1 prediction interval to this patient. Okay, easy to interpret, and it should have the semantics that whether our patient interprets this as a marginal coverage guarantee over the first group, or the second group, or the third group, she is correct either way. All of those interpretations are simultaneously correct. Okay, that's the goal of group conditional coverage. Okay. There's something else I could want, which is sort of calibrated coverage. Because if you think about it, if I just ask for group conditional coverage, there's a way I can cheat that is not very interesting. I could sort of say, okay, I'm going to produce a randomized prediction set by picking a threshold at random. 95% of the time, I'm going to pick the threshold to be infinity. It's going to cover all of the labels. 5% of the time, I'm going to pick the threshold to be minus infinity. It's not going to contain any label, and it'll, on every example, cover the label 95% of the time. But this was not very interesting. Okay, but the issue, of course, is that I cover the label 95% of the time, in expectation over the threshold, but not conditional on the threshold. So to stop me from doing this, I'm also going to ask that my guarantees hold conditionally on the threshold. Okay, that's threshold calibration. And what I'm going to do ultimately is ask for both of these things at the same time, something I'm going to call prediction set multi-validity. I want my prediction sets to cover the label 95% of the time, not just marginally, but also conditionally on the group and conditionally on the threshold. Okay? Now, if you've heard of something called multi-calibration, that's about predicting means in a way that has no statistical bias, conditional on groups and conditional on the prediction. What's going on behind the scenes here is a quantile analog of multi-calibration. If you like, what we're doing here is multi-calibration, but rather than for means, for quantiles. Okay, so how do you do it? So if you just want group conditional coverage, if you don't care about threshold calibration, it is super duper easy. Okay, you just solve a single convex optimization problem. What do? Well, you really just solve a quantile regression problem. You minimize something called pinball loss. If you haven't heard of pinball loss, you've probably heard of absolute loss, just the absolute value. Okay, the thing about absolute loss is if I minimize absolute loss over some distribution over constant predictions, that'll be minimized at the median of the distribution. It elicits the median of the distribution. The median is the 50th percentile quantile. There's nothing special about the median. It turns out if you tilt the function a little bit, you'll elicit different quantiles, and those loss functions are called a pinball loss, because I guess pinballs would, kind of do that. Okay, so you just minimize pinball loss over what? Well, you minimize pinball loss over functions that are linear combinations of the indicator functions for the groups that you care about. Okay, so for every group, there's a coefficient. You learn, you just fit, if you have G groups, these G coefficients that are functions of just linear combinations of these group indicator functions. If you do that, the model you get out will satisfy group conditional validity. Okay, this is a in distribution statement, but you can get a generalization statement with sort of standard techniques. Okay, what if I want threshold conditional coverage as well? Okay, so full multi-valid coverage. It's no longer a one-step optimization algorithm, but there's a pretty simple algorithm, an iterative algorithm, which you can analyze again as gradient descent on pinball loss. Okay, it's iteratively producing a model, again, somehow as a function of the group indicator functions. And what you can show is that this quickly converges to full multi-valid coverage. Okay, so it quickly converges to getting coverage guarantees, not just conditional on the groups, but conditional on the threshold as well. So no cheating. Okay. So let me tell you about the online problem. Okay, so far, like I told you, I was going to walk you through these sort of three kinds of results. First, I was going to ask for stronger than marginal guarantees, but there's still a distribution, right? We're still talking about a distribution. Now I want to ask for these same stronger than marginal guarantees, but I don't want to assume there's a distribution. I want to be able to handle the case in which the profile of examples that I encounter can change drastically and arbitrarily over time in ways that I do not anticipate. Okay, so what's the model in which we're going to think about that? It's sort of an online adversarial model. Okay, so here's the setup. Time proceeds in rounds 1 through capital T. In every round, an adversary selects a feature vector, xt, and shows that to the learner, and also selects a label but doesn't show that to the learner. Then the learner chooses a threshold on the nonconformity score, which in turn implies choosing a prediction set. And only at that point does the adversary reveal the label. And at that point, we learn whether the prediction set covered the label or not, and in particular, we learn what the nonconformity score of that label was. Okay, so this is an adversary. The adversary can make arbitrary choices it's even an adaptive adversary. They can be making choices in response to what the learner has done. By the way, the reason to study a model like this is not because we necessarily believe that there is an adversary, but rather if we can prove positive results in a model in which there's an adversary, in which we've made no assumptions, then we don't have to worry about in deployment that our assumptions might have been violated. Okay, this is going to be a very robust model. Okay, and the goal is that in hindsight, right, when this is all played out at day t, we have some empirical distribution on predictions and realized labels. In hindsight, I would like on this empirical distribution that my predictions will have satisfied this notion of multi-valid coverage, that I should have covered the labels 95% of the time, even on those subsequences that were restricted to some particular group, even on those sub-subsequences that were restricted to some particular threshold. Okay. How would you do such a thing? So let me quickly remind you what a zero-sum game is. Rock, paper, scissors. More generally, in a zero-sum game, there's two players, the minimization player that I'm going to identify with a learner, and a maximization player that I'm going to identify with an adversary. They both have finite strategy spaces. And there's some utility function that maps actions from the learner and the adversary to some number. The minimization player would like that number to be small. The maximization player would like that number to be large. And the thing you should know about zero-sum games, if you know only one thing about zero-sum games, is the minimax theorem. Okay, the simplest version is von Neumann's minimax theorem, which applies to finite games, and you can get fancier versions as well. But what the minimax theorem says is that the order of play doesn't matter. Okay, we don't have to play simultaneously. It could be that the learner first has to commit to their strategy and reveal that to the adversary, and the adversary could have the luxury of best responding. Or it could be that the adversary had to commit to their strategy and reveal that to the learner, and the learner could have the learner would have the luxury of best responding. And what the minimax theorem says is that how well you can do in this game, assuming you play optimally, is invariant to this ordering. You can do just as well if you go first compared to if you go second. Okay? So the basic idea is to define a game between the learner and the adversary, where the strategy space for the learner is the set of prediction algorithms that they can use. The strategy space for the adversary is the set of algorithms mapping transcripts of what's happened so far to feature label distributions. And the objective is essentially your multi-validity error at the end of this transcript. Okay, your objective in the end, the learner will be happy if their coverage rates for every group and threshold are close to 95%. The adversary will be happy if they're far from 95% for any group or threshold. Okay? Now, what's really happening when we claim that there's an algorithm that works well against any adversary is that the learner is going first. The learner, us, is committing to an algorithm. That's the algorithm that we write in our paper. And the claim is that even if the adversary best responds, even if the adversary produces the sequence that is worst for this algorithm, that we do well. Okay, so to make a claim like this, we are operating in the setting in which the learner goes first. But to think about how well you can do in such a setting, what the minimax theorem tells us, assuming we've been careful to satisfy the conditions of the minimax theorem in our construction, is that we can analyze it as if the adversary goes first. Now, what does it mean that the adversary goes first? Well, in this case, what it means is that every day before we need to make our prediction, okay, after we've seen the features, the adversary tells us what is the distribution on the nonconformity score. Now remember, our goal is to predict the 95th percentile quantile of the nonconformity score distribution. This is very easy to do if we've already been told it. Right? If the adversary has told us the distribution, then if we want to get 95% coverage, all we need to do is look at the distribution and read off from it the 95th percentile quantile. So in the world in which the adversary goes first, it is very simple to see that it is possible to get multi-valid coverage because it's just about correctly predicting a statistic about the distribution. It's much easier to predict something that you already know the answer to. And non-constructively, at least, the minimax theorem tells us that it's possible to do just as well if you have to go first. There is an algorithm that does as well on this metric as if as you could have done had you seen the distributions you needed to predict ahead of time. Now, of course, this is non-constructive so far. The minimax theorem doesn't give you the algorithm. It tells you something about the value of the game. But okay, let's go on. What is the theorem you get out from it in the end? It is this. Okay, there exists an algorithm. So far, we don't know what it is. We'll see it in a moment. There exists an algorithm such that for any collection of groups, okay, you could have a lot of groups, they can intersect. And for any sequence of models that you're going to use to predict, and for any sequence of nonconformity scores, all of this can be chosen by an adversary. And for any sequence of examples, we have the guarantee that if in hindsight we look at our empirical coverage, the frequency with which the label is contained within the prediction set, and more than that, we don't just look at our marginal coverage, but we zoom in just on those rounds for which the example was a member of one of the groups, and we further zoom in just on those rounds for which we predicted a particular threshold, that our empirical coverage will be close to our target, 95%. How close? Well, it'll deviate by 1 over the square root of the length of the subsequence, the number of examples we've seen who are members of that group and for which we predicted a particular threshold. This is the statistically optimal rate, even in a distributional setting, in that if I knew what the distributions were and predicted exactly the 95th percentile quantile every day, then on any sequence, my empirical coverage would differ from my expected coverage, which is 95%, by like 1 over root the length of the sequence. It's not surprising you get the statistically optimal rate, because the way the minimax argument works is by placing you in a position of actually knowing the distribution. Okay, but without any assumptions at all, okay, this could be an arbitrary sequence, you can get these conditional coverage guarantees at a rate that would be statistically optimal even if there was a distribution and you knew it. Okay. You might worry when you see like a non-constructive argument like that, that you know, the algorithm is hard to come by. But in this case, actually, you can get a closed form for the algorithm, right? Like it's clear what you need to do at this point. You need to solve the minimax equilibrium of this game we've defined, and you can do it. And in fact, the algorithm is sort of simple. Okay, so here it is. I'm not going to walk through the details except at a high level to show you that it's not complicated. So like, what do you do? Well, in each round, for each of the possible predictions you might make, you compute a number. Okay, what is that number? Don't worry too much about it, but that number basically is the sum over all of the groups you want coverage of some quantity that depends on your empirical coverage on the subsequence that has occurred so far for members of that group for whom you've made a particular prediction. Okay, so you just compute a number from the history. How many numbers do you compute? 1 for each quantile value you might predict cross the number of groups you want multi-valid coverage with respect to. And then you just do some algebra. You compute like the signs of these numbers. You find a pair of adjacent predictions whose numbers have opposite signs, and you carefully randomize between those two predictions in some way. Okay, the only, like, the computation here is really dominated by like this first step where you're computing these numbers. So the running time, you have to sum over all of the groups, and so the running time here is like linear in the number of groups. And so if you have a lot of groups, that'll be slow. If you have a few groups, that'll be fast. Everything else is just arithmetic. Okay, third result. So here's a map of something. I told you about the existence of this thing called multi-calibration, which, if you've heard of it, great. If you hadn't, it's a lot like multi-validity, but for means instead of quantiles. Like basically, multi-calibration asks for a predictor of the mean of the label distribution, such that the predictor is statistically unbiased, not just overall, but conditional on membership in a group and conditional on the prediction itself. I just showed you algorithms that in the online and adversarial setting can get quantile versions of multi-calibration. By the way, you can do both of this stuff for mean multi-calibration as well. And so you might now wonder, you know, okay, like there's means, there's quantiles. Those are not the only two properties of distributions. Is there some notion of property multi-calibration for other properties you might care about? Okay, there's other things you might care about even for the problem of quantifying uncertainty, variances, higher moments, other things. And so we can define what it would mean to be multi-calibrated with respect to some other property. Okay, so what is a distributional property? It is just some mapping from distributions to numbers. It's just some way of labeling distributions with numbers. So the mean is a distributional property. I can label distributions by their mean. So is quantile, a variance, conditional value at risk, any way you know of computing a number as a function of a distribution, that's a distributional property. And I could have a predictor that purports to predict that distributional property for a conditional label distribution. The predictor would take as input a feature vector and would output a number that purports to be the distributional property for the conditional label distribution. And I could say that my predictor was not just marginally correct, but was multi-calibrated for that property with respect to a set of groups. If my prediction, if I look at the set of all examples for whom I predict V that are also members of some group G, okay, and then I look on this conditional label distribution of the distributional property that I predicted was V, it really should be V. Okay, it says that conditional on the value of my prediction and on membership in a group, my predictor should be correct about the distributional property. Okay, that generalizes mean and quantile multi-calibration. Okay, so, okay, that's a definition, but like, when can we do it? Okay, so let me give you some jargon that maybe, if you're a statistician, what I'm going to describe are M estimators, except I'm going to use the terminology that comes from sort of the economics literature, which is about property elicitation. Okay, so a property, and this is sort of, the reason it's called elicitable is what these guys are interested in is sort of writing contracts that will incentivize you to tell me the property if you know it. Okay, so a property is said to be elicitable if there is some regression function, if there's some loss function mapping examples and numbers to real values such that when I solve like the empirical risk minimization problem in expectation over the distribution, I find the value that minimizes this regression function in expectation over the label. The value I get should be equal to the property value on the distribution. Okay, so these are M estimators, if you're familiar with that term. Okay, so means are elicitable because squared error has this property. Squared error regression elicits the mean. Medians are elicitable because absolute loss regression elicits the median. Quantiles are elicitable because pinball loss elicits quantiles, but not everything is elicitable. Variance is not elicitable. Skewness is not elicitable. Plenty of stuff is not elicitable. Okay, so here's the first theorem. If a property is not elicitable, then you can't multi-calibrate with respect to it. In fact, you can't even calibrate. Like, there exist distributions such that no predictor satisfies calibration on that distribution for that property. Okay, so it's not about computation, it's about existence. Like, the definition is just sort of like incoherent for non-elicitable properties. On the other hand, if the property is elicitable, then for any collection of groups, there is an efficient algorithm, sort of a canonical efficient algorithm. It looks a lot like the algorithms I've shown you that do efficiently multi-calibrate with respect to that property, both in the batch setting and in the online adversarial setting. Okay, so you can find a multi-calibrated predictor for a property if and only if that property is elicitable, if and only if it's an M estimator. Okay, and when you can do it efficiently, both in the batch setting and in the online setting. If you really liked variance, this might sound like bad news, because variance is not an M estimator. But, okay, a little bit of good news, because here's something that I don't know of sort of equivalent M estimator terminology for. This is why it's useful to use the elicitation terminology. Suppose I've got two properties, gamma 1 and gamma 2. I can say that gamma 2 is elicitable conditionally on gamma 1 if for every value of the first property, gamma 1, if you promise me that the distribution you give me has property value on the first value equal to gamma 1, then subject to that promise, there is a regression problem, an ERM problem I can solve over the distribution whose solution will be the value of the second property. Okay, so it'll give me, it'll say, I can solve a regression problem to learn the second property under the promise that you've told me the value of the first property. So means are elicitable. Variance is not elicitable, but variance is elicitable conditional on the mean. If you tell me the mean, I can elicit variance. Quantiles are elicitable. Conditional value at risk, which is a financial risk measure that sort of says, what is the expectation of the distribution conditional on being in the 10% tail? What's the expectation of my loss in the 10% worst examples? It's not elicitable, but it is elicitable conditionally on the quantile. Okay, so suppose you have a pair of properties, gamma 1 and gamma 2, such that gamma 1 is elicitable, something like a mean or a quantile, and gamma 2 is elicitable conditionally on the first one. Okay? Something like variance or conditional value at risk. Then what you can do is you can learn a two-dimensional predictor. Takes as input features, outputs two numbers, like a mean and a variance, or a quantile and a conditional value at risk, a two-dimensional predictor that will be jointly multi-calibrated on these two distributions. By which I mean, if I look at all of the examples for which I predicted that the mean was 0.1 and the variance was 0.05, that when I condition on both of those things at the same time, I will have been correct. The mean will have been 0.1 and the variance will have been 0.05. And I can condition on groups as well. That's the multi-calibration part. I can condition on both of these properties and groups. And again, there's an efficient algorithm that achieves this for any pair of jointly elicitable, or for any pair of properties such that the first one is elicitable and the second one is conditionally elicitable. Okay, so you can do variance if you also do mean. You can do conditional value at risk if you also do quantiles. Okay, so how much time do I have? 10 minutes, okay. So the nice thing about this stuff, which is not true of everything I do, so I want to take advantage of it when it is true, is that these are like real algorithms that you can actually run. So let me show you some experiments. Okay. So here is, here's an experiment run on data derived from the 2018 California census. Okay, so this is an income prediction task. If you know the adult data set, this is like a fancier version of the adult data set. Like, it's all of the data instead of having been condensed down to 50,000 examples, and it's the real valued labels, not binarized ones. Okay, but you're sort of, if you heard of adult, you know the kind of data this is. Okay, 2018 census data, the task is income prediction. And it's census data, so we have demographic attributes. Okay, so we have self-reported race and gender. Okay, these are intersecting groups because each of you has both a race and a gender. And so you can run various conformal prediction techniques. The simplest thing you could do is just the sort of split conformal prediction method that I sort of outlined for you early on, that entirely ignores group membership. It just finds this like single threshold that is this marginal 95th percentile quantile. Actually, here we're aiming for 90% coverage. That's the blue line. And when you do that, what you see is that although it gets 90% coverage marginally, once you condition on the groups, it doesn't anymore. So on some groups, it's substantially overcovering. That's kind of making up for the fact that on other groups, it's substantially undercovering. Okay, this was sort of the concern of our patient, that marginal coverage does not promise coverage once you condition on things you know about the patient. There's another thing you could do from the literature, which is be conservative. You could compute a threshold separately for each group that corresponds to the 90th percentile quantile for that group. That would be the right quantile to use if the groups were disjoint. The problem is, if they're not, if you have both a race and a gender, do I use the quantile for the race or for the gender? The conservative thing to do is to use the higher of the two. Okay, that will always guarantee 90% coverage, but it's conservative. That's what the purple line is doing. Indeed, the coverage you get is always above the target, but sometimes it's well above the target. Or you could use our method. I showed you two methods. These are the sort of distributional methods. One just gets group conditional coverage, the other gets threshold calibrated coverage. The one that just gets group conditional coverage is this one. The one that gets threshold calibrated coverage is this one. And what we see is that they hit their coverage targets, like conditionally on the groups. Okay. You could also compare prediction set sizes. Okay, like, you know, we don't just want coverage, we want coverage that is with small prediction sets. And, you know, sort of what you see is that, okay, like, split conformal prediction produces smaller prediction sets when it undercovers, which is to be expected. That's how it's undercovering. But in general, like, these methods that are using group membership to get a correct coverage, well, the way they're getting correct coverage is when the other methods overcover, they are successfully getting smaller prediction set sizes. They are taking advantage of the fact that there's more signal in some of these populations. You can also measure on the same data the threshold conditional coverage. Okay, so again, the methods that split conformal prediction, there's only one threshold, so it has threshold calibrated coverage by definition marginally, although not separately on the individual groups. Our iterative method, the dark green one, which is trying to get threshold conditional coverage conditionally on the groups as well, in fact does. You can hardly see the line on most of these. The interesting thing is that this much simpler algorithm, this sort of one-shot quantile regression algorithm, which doesn't promise threshold conditional coverage, just promises a group conditional coverage, actually does pretty well here as well, for reasons we don't entirely understand, but, you know, we're happy about. Okay. Oh, and you can run the online algorithm too. Okay, and so one way to evaluate the online algorithm is with unanticipated distribution shift. Right? It's not really an adversary, it's just that at some point the distribution changes and you don't know when or how, you don't know anything about the change in the distribution. Okay, we should be okay in that case because that is just a special case of an adversary. And so we run this sequential prediction task on the same census data, except initially we're presenting data from California, and then at some point we switch to data from Pennsylvania, which is not totally different. Like, California is kind of like Pennsylvania, but like it's not exactly the same. And so what you see is that split conformal, you know, which just ignores, does not attempt to take advantage, it does not attempt to address the distribution shift, and how could it? It doesn't know anything about it. Overcovers, whereas our online method comes much closer to the coverage target despite the distribution shift. Okay, so let me wrap up there. This stuff, if you want to learn more about it, is kind of, I've been having fun thinking about this for a while, so it's sort of, you know, some of the early theory stuff, you know, is in these sort of earlier papers. The practical algorithms, the online algorithms, are in this NeurIPS 2022 paper. The batch algorithm is in this iClear paper from last year. The code for these things is available. And then this characterization of distributional properties and when you can and cannot multi-calibrate with respect to them, that's sort of a theory kind of paper in ICML. And I taught a class on this stuff and came up with like a detailed set of lecture notes if you want to read about it, and it has this memorable URL, uncertaintyclass.com. You can check it out and, you know, learn more about this than you ever wanted to know. Thank you.
Thank you, Aaron, for the great talk. So I think we have about 10 minutes for questions.
Thank you, great talk. I have two questions because I'm not too familiar with the literature. So basically these are like curiosity questions. So I am aware of a series of conformal works by Jing Lei, then Larry Wasserman, Condes, Tibshirani, and others. doesn't that line also provide conditional guarantees, or?
No. So there are a few papers that think about conditional guarantees. Yes, so basically there's, in the prior work, there's two ways of dealing with conditional guarantees. One is, okay, if there's a paper by some of the folks you mentioned that handles the case when the groups are disjoint, where you can essentially separately calibrate on them. Then there's a paper also by some of the folks you mentioned that thinks about what to do when the groups intersect and proposes this conservative thing I mentioned, which is the purple baseline here, that you can calibrate separately on each group and then take the highest threshold. And then recently, Candace and his students have followed up on some of our work and have given elaborations on this kind of multi-valid coverage.
I see. Okay, thank you.
Other questions?
Thank you for the nice talk. I have two quick questions. The first one is, you were motivating the condition on the first part, conditioning on the threshold as a way to sort of leave aside this pathological case where you could have infinitely large intervals. Do you really, but then, when you showed results, they kind of perform the same. And so what I'm wondering is, do you really need to condition on the score? And like, maybe you can get away without conditioning and just algorithmically asking for the minimal interval length that satisfies your conditional coverage?
Yeah, so let's see. So at least on these data sets, empirically, the simple quantile regression kind of algorithm didn't do too badly on the threshold conditional coverage, even though it wasn't guaranteeing it. You can cook up algorithms and probably data sets that do that. In the end, right, like, conditioning on more stuff is always better to the extent that you can do it. It is sort of a funny thing to condition on the threshold, because that's sort of part of the internal workings of the prediction set. So one thing we know how to do now that we didn't know how to do at the time that I made these slides, is what you can do is you can condition also on the size of the prediction set. Okay, so you can condition on, which is sort of closer to the thing that you want to condition on. You can get coverage when the prediction set contains one label. You can get coverage when the prediction set contains two labels. And I think that also prevents cheating, and it's more natural than conditioning on the threshold.
Cool. And then to the result of properties that you can elicit as solutions to ERM problems, there are some quantities that you can elicit, others that you can't. The ones that you can't, can you elicit them approximately?
No. Yeah, I mean, I guess, okay, the short answer is I don't know. The medium answer is I don't know, and it would probably hinge a lot on what it meant to elicit them approximately, and you'd have to deal with issues of scale, like, are we talking about multiplicative approximations? But the thing that's driving this result, by the way, is a very nice characterization that says, if your distributional property is not an M estimator, if it's not elicitable, then its level sets are not convex. So I could have distributions that have the same property value, but then when I take convex combinations of these distributions, the property value changes. That's not true for means or quantiles, but it is true for variance, for example. And so, somehow conditioning on things that are short of everything, conditioning on groups rather than exactly the features, involves taking mixtures of distributions, all of the conditional label distributions for conditional on features that lie within this group, and the non-convexity of the level sets is sort of what breaks calibration.
Thank you.
Another question?
Yeah, thanks so much for your talk. Actually, I had two questions. One is just, I was wondering if the online adversarial algorithm ends up being conservative if there's not really an adversarial behavior, like if, for instance, no distribution shift. And then the second one was on if you're targeting both the mean and the variance. You mentioned you might, or what I took away was you might need to get the mean to get the variance, and if you're jointly getting those two targets, if you need to do some sort of multiple testing correction because you have two targets.
Yeah, so like for your first answer, I mean, I think for your first question, I think the answer is sort of in theory no, but in practice yes. Like the asymptotic bounds are the thing you would get even if you knew the distribution. Now, hiding in those asymptotic bounds are constants, and if you actually knew the distribution, you'd be better off calibrating specifically to that distribution. For your second question, I think the answer is no, although maybe I didn't totally understand. What the algorithms look like, they're sort of like alternating minimization kinds of algorithms. You sort of calibrate to the mean, and then conditioned on the mean predictions of your mean calibrated predictor, you calibrate to the variance. And then conditioned on the variance predictions, you recalibrate to the mean. And you go back and forth, and you prove that this converges.
As a question, Dad? Any other questions? I have one. So when it comes to distribution shift, which is one of my domain, so that I want to ask that question, right? So the question is similar with Drew's one, but then I want to understand a bit more in terms of like why, in theory, that if you know something that you can directly calibrate to, that you still get the same kind of theoretical guarantees.
Let's see. So maybe I didn't understand the question.
Like you said, when it comes to like distribution shift, if you know something about the exact distribution, and if online maybe it's a bit more pessimistic, so then can you improve the theoretical guarantees you get when
yes,
you?
So like maybe you could improve the constants.
Yeah.
So asymptotically you can't. You're getting the right rates, but the constants are going to be bigger given what we currently know compared to if you calibrated directly to it. But by the way, the biggest weakness of these online methods is that they need feedback, right? Like at the end of each interaction, after I make my prediction, I need to learn what the label is. So there's no division between train and test in these online methods. And so they're great when you can run them, but they only apply in settings where you get feedback about what the label is after you make your prediction, which is probably just a small subset of settings. It makes sense for like stock prediction and maybe some other stuff, but if the point of making your predictions is that you don't know the labels, then they don't work. And then you need to think more about more traditional distribution shift methods.
Got it. Any more questions? Oh.
Thanks. I wanted to ask just about the basic idea, because I got marginals and conditionals floating around all over the place. So if I did something simple like a regression and I had 3 features and I conditioned on them, I should get a prediction interval that should have the stated properties conditional on those 3 features, but marginal over whatever is not in the model, right?
So careful, because...
Yeah, so that's what I wanted to ask about.
So sort of by using classical techniques in like linear regression, you can get prediction intervals if the assumptions of the ordinary least squared model are satisfied.
Sure.
So that's true. We're trying to do this non-parametrically without making any assumptions about the world. So if you assume the world is linear, then you can estimate the parameters of your linear model and translate those into prediction intervals. In fact, then you get things conditional on all of the features. If the
in some sense, you could just run a model that's marginal on each of those features, right? And then take the union of those prediction intervals, for example. And how is that going to relate to what's optimal here? Because in some sense, then you're marginalizing. You've got the marginal prediction interval for each feature. You don't need the assumptions of whatever the new model looks like, whether or not. And then you're just extending your interval. So in some sense, you're overcoming.
Yeah, so the main so if I understood correctly, and remember these are not, I just want to make sure we're disambiguating between confidence intervals on the parameters and prediction intervals on the predictions. What you're proposing would overcover. Like you can take the union of these things, but you might, if you were aiming for 90% coverage, you might get 100% coverage.
Yeah, I mean, probably wouldn't get 100%. That would be the whole space. But we could easily recalibrate that. I'm just trying to connect that to what the optimal strategy is. Because in each of those cases, you got back to the want whatever that marginal is without having a really fast path.
Yeah, if you have some method of doing this with linear regression, I'd love to hear it. I don't know of such a method.
Okay, I mean,
Yeah.
So we have 3 contributed talk coming up. Just do the list. Okay, our first contributor talk is from Ganesh, who is going to talk about supervised contrastive loss length, orthogonal frames, and batching matters. Okay, cool. Go ahead.
Hi everyone, my name is Ganesh. I am a PhD candidate at UC Santa Barbara. So in this talk, I'll be talking about symmetric neural collapse representations with supervised contrastive loss, the impact of ReLU and batching. So the outline is going to be like this. I'll first start with a brief background on the topic. So the agenda of the talk is to try and understand the following. That is, if we train a multi-class classifier, a DNN model for performing K-class classification with a certain kind of loss function, then does the optimization over the loss function impose certain optimal structures in the DNN? So a pioneering study by Papian and others in 2020 called this the neural collapse. So what we want to focus on in this talk is the impact of class imbalance on these structures. So prior works in this domain with cross-entropy loss and similar losses have shown that such a structure that emerges during training is quite sensitive to class imbalance. I want to talk about a way to get invariant feature geometry invariant to the class imbalance in the specific loss function, which is a supervised contrastive loss, or the SCL in short. So additionally, in contrastive losses, batching often plays a critical role. So we want to explore the role of batching in neural collapse in SCL. So the setting is this, very simple. We are all really familiar with the setting. That we have a K-class classification problem, and we train a neural network to get a mapping from the input to the feature space, and then we predict using some kind of argmax function, standard stuff. So here's a schematic of a DNN that is used for classification over K classes. We are particularly interested in the feature embeddings in this talk. And a little bit about the classifier head as well. So when training a model for classification with the cross-entropy loss, we typically learn the feature map and the classifier head jointly. Whereas the supervised contrastive loss is an alternative solution that was introduced relatively recently. With SCL, during training, we actually just learn the feature maps only. And then for classification, you can use your favorite classification rule like nearest class center or SVM and the like. So in a pretty remarkable study, Papian and others asked the following question. Suppose we train a DNN for K-class classification. Is there any predictable structure that emerges in the trained model? And can we say something about the geometry of different vector quantities in the model, things like feature representations and classifier weights and so on? So they showed that the answer is yes, specifically with balanced training data and cross entropy loss function. An optimization phenomenon was observed that they termed as neural collapse. In short, this refers to the fact that as training progresses, the feature embeddings for all examples belonging to a particular class tend to collapse into one point in space and away from other classes. Not only that, the class mean embeddings form a geometric structure called the simplex equiangular tight frame. For our purposes, it is that structure that kind of maximally separates k vectors in a space that is at least k minus one dimension. So since a natural question then was to ask if this geometry remains if the classes were imbalanced, we were interested in exactly that. So in this previous work, we showed that a more general geometry emerges that we termed the simplex encoded label interpolation, or SELI in short, whenever the training data is class imbalanced. So the neural collapse paper really pioneered this recent interest in trying to explain and predict these geometric structures that emerge and that govern the training endpoint of various DNN models. So several works have followed up that initial study. So let me say a little bit more about the cross-entropy loss with class imbalance. In this 2022 paper, we derived a closed form expression for those exact angles and norms for features as well as classifier geometries for any given imbalance ratio. So R here or in later slides will represent the imbalance ratio, which is simply the ratio of the number of examples in the largest class to the smallest class. So empirically, we trained DNN models on different data sets with varying imbalance ratios and showed that the geometries converged closer to the SELI geometry that we predicted and away from the simplex ETF. Now let's turn to the supervised contrastive loss. So for balanced data, Graf and others showed that showed using an unconstrained features model as a theoretical model that SEL, the supervised contrastive loss, behaves similarly to the cross-entropy loss whenever the data is balanced. An important aspect of the SEL is that the loss function optimization depends quite a bit on the mini batch selection. So since you contrast pairs of examples that are present in one particular batch, the way these examples appear in different batches makes things a little bit more interesting and also complicated. So in fact, the proof in this paper requires you to consider all possible combinations of examples of a given batch size B, which is n choose B number of mini batches, which is pretty large. It's a very nice proof, but is definitely harder than that for cross entropy. The assumption of balanced data helps keep some things somewhat in control. So due to this complex interaction between batches and examples, it's not very clear. It's not clear what is the geometry when the classes are imbalanced. So it can be argued to be different from the simplex ETF, easier to see in this simple DNN experiment, for which this plot is shown here. Here we have a ResNet model trained on MNIST. We compute the class means of the features at the end of the training. So we have 10 classes, and hence, so we plot the gram matrices of these inner products between the 10 class mean vectors, or the gram matrices of the class mean vectors. So 10 classes means 10 by 10 matrices. I think 5 of these were majority classes and remaining 5 were minority classes. For R equals 1 balanced data, SEL and cross entropy features are quite similar. The inner products are those between classes which are the off diagonal entries, which are quite small and are exactly given by the ETF geometry. For R greater than 1, the cross entropy loss can be predicted, these figures on the right, can be predicted by the SELI geometry that we saw in the last slide, which varies with class imbalance. The SEL also empirically, as we see here, the geometry varies with class imbalance, but we do not yet know what to compare it with. So that is what we want to try and answer in this paper. So then we repeated the experiment of SEL, now with ReLU applied to the last layer features. In the previous plot, or even in this plot, the second column is without ReLU on the last layer features, but now we repeat the same with ReLU. So now surprisingly, the gram matrices always converge to identity. The diagonals are 1 because of the normalization, but the off diagonals are 0 because the class means end up being orthogonal to each other, regardless of class imbalance for r equals 1, 10, or 100. This structure is called the orthogonal frame, which is similar to the ETF in the sense that if we remove the average of these vectors, the orthogonal frame just reduces to the ETF. So in summary, the empirical observation is that we are able to see a geometry that is invariant to class imbalance if we train with SEL loss, but with ReLU at the last layer. So the plots shown before were one way to visualize, especially when we do not yet know the target geometry. But now that we think the target geometry is the orthogonal frame, we can simply plot the residual distance of our empirically observed gram matrices from the identity matrix, which is the gram matrix for orthogonal frame. So we observe consistent convergence of features to OF geometry across different data sets and different imbalance profiles. And also, interestingly, this is much cleaner than what we saw for the features converging to their respective target geometries in the cross entropy loss. So having seen this surprising empirical observation, we now try to support this with theoretical analysis. So several prior works have successfully used what's called the unconstrained features model, or the UFM, to explain and predict the neural collapse geometry for different supervised loss functions. Now we extend the UFM to mimic ReLU at the last layer by having these element-wise non-negativity constraints on the features. For simplicity, we just call this UFM plus. So our first main theoretical result is this, that if we perform SEL minimization with all examples in the dataset being considered as one single batch, and if the ambient space is space has dimension at least the number of classes, then we get a lower bound as shown here. This lower bound is tight and is achievable if and only if two of these conditions happen. The first one is that the intra-class variability collapse happens, which is also part of the original neural collapse. And also that the class means form an orthogonal frame geometry. The proof idea is mainly sequential application of inequalities such as Jensen's inequality and Cauchy-Schwarz. Moving on to the more interesting case of mini batch optimization, because typically that's what we do when we have a contrastive loss. Here we assume that we are given an arbitrary set of mini batches to work with. And with that arbitrary set, we prove the corresponding tight lower bound again. Let's recall that in case of SEL without ReLU and even the simple balance data, Graph and others had shown that showed a similar lower bound, but they had to consider the specific set of mini batches, which is basically all combinations of examples of a given batch size. But now with just a simple ReLU applied, we are able to get an achievable lower bound for an arbitrary batching. So the equality conditions are simply that in every batch, the examples from the same class should correspond to the same feature vector in space, but examples from different classes must be orthogonal. So it could be tempting to say that the global minimizer here again, like the full batch case, is also the orthogonal frame, but there is a subtle issue, and we'll talk about that now. So to answer the last question, whether OF geometry is still the global minimizer with mini-batch optimization, let's see it through a simple example. Let's consider three classes: red, yellow, and blue. Red has example indices 1, 2, 3, 4. Yellow has 5, 6, and blue has 7, 8. But now we have two mini batches, one that has the examples 1, 2, and 5, 6, and the other examples 3, 4, and 7, 8 belong to the second mini batch. We can perform the SEL minimization with these two mini batches, and with the previous theorem, we can get equality conditions for the same. It's easy to check that something like this configuration does satisfy the equality conditions of the theorem. But what we can see here is that it violates both the conditions for our orthogonal frame geometry, which is variability collapse inside a class. That is, the red examples are now not collapsing to the same point. Also, the orthogonality between, say, blue class and this red examples. So turns out we can draw many such configurations which satisfy the equality conditions, and orthogonal frame structure being one of them. So the point is that the minimizer geometry is not unique. So then a natural question would be, can we identify scenarios in which we do get a unique global minimizer, and that being the orthogonal frame geometry? That is what we show in the following corollary. A graphical approach is quite suitable to describe something like this. So we define what's called the batch interaction graph to capture these direct and indirect relationships or interactions between examples, either through being in a common mini batch or through a common link across many batches. It's a simple graph where vertices are example indices and two vertices are connected if basically those two examples are present in at least one mini batch. Without going into like full details of this corollary, essentially these two graph connectivity conditions are necessary and sufficient for identifying whether or not a given arbitrary mini batch scheme, a batching scheme, does give us a unique minimizer. So we can check that the sufficient condition of all combinations of examples from the earlier paper is a special case of these two conditions, but this requirement now is much more relaxed. So having identified the necessary and sufficient conditions for a batching to give OF uniquely, we turn to an algorithmic question. Suppose we have an initial batching scheme given to us, that is, someone has given us a set of mini batches to work with. For example, a popular choice in practice is just having just partition the example indices and then use those as mini batches. Because these are like partitions, it's a partition, we can check that they violate the conditions of our corollary and hence won't give orthogonal frame geometry. So starting with this batching, can we turn it into one that does satisfy the conditions and hence gives OF geometry? Turns out there's a rather simple answer, at least one of them. We simply pick an example each from every class and keep these fixed set of k examples, if k is the number of classes, put them in all of our mini batches. So this scheme, we call it batch binding, and there's a schematic figure to explain this or depict this. In practice, we do observe that in DNN experiments, if we perform batch binding, which is the rightmost column here, remember these are the residual distance plots from orthogonal frame geometry, we get a very stable behavior of convergence to OF. In comparison, if we only have this partition mini batching and even keep them fixed across optimization epochs, then we don't necessarily get OF, as we see in some of the curves here, which we can explain using the corollary. And something in between, suppose we do perform the common practice of shuffling around these partition mini-batches in between two optimization epochs. Because of an averaging effect, we do get OF eventually, but we can see that it's not as clean as with batch binding. So it's probably useful to highlight the impact of ReLU in our study. In presence of class imbalance, having ReLU symmetrized the feature geometry and gave us an invariant structure. From a theoretical point of view, the key reason that allows us to have a more relaxed batching condition than the prior work is that with ReLU, the individual mini-batch minimizers are also allowed to be the joint minimizers, and that's not the case at all without ReLU. So this is why we get a more relaxed condition. In terms of generalization, we did experiments and noted in our paper that adding ReLU does not hurt test performance. In some cases, in fact, improving it, while giving symmetric features for free. In summary then, for the first time, we have characterized the feature geometry of supervised contrastive loss with class imbalance. We observe that we get invariant feature geometry. Our theoretical analysis is through an extended UFM model to include non-negativity, and we conduct extensive experimentation to support this hypothesis. And finally, we have uncovered the effect of batching in this neural collapse geometry for SCL and give a method that always gives us OF minimizers. So hopefully this study inspires further investigations into the nature of SCL and lead to algorithmic improvements. Finally, I'd like to thank my advisor, Christos, and wonderful collaborators. I'd also like to invite you to take a look at our paper and reach out with any questions or comments. And finally, thanks to the organizers for this wonderful workshop.
So we ran out of time, so I will not take the questions for now, but we have a poster, right, in the poster session. Do we have a poster in the?
I'll be around.
Okay, yeah, but just to remind you that we have a poster session at 5 p.m. and then people can ask Ganesh questions and talk more and leave all the questions maybe to the poster session. Yeah, thanks a lot. So our next speaker will be Xinyi, who will be talking about can graph attention prevent over-smoothing?
Can you guys hear me? Okay. Hello, everyone. I'm Xinyi. I'm a grad student from MIT. So from now, I'm going to shift the gear from neural collapse to another well-known rank collapse phenomenon in graph neural networks called oversmoothing. Specifically, I will be talking about oversmoothing in attention-based graph neural networks, including our well-beloved transformers. So this is a joint work with my wonderful collaborator, Amir Zihui, and my advisor, Professor Ali Jababai. So message passing GNNs and transformers, where the latter can be viewed as message passing GNNs on complete graphs, are known to suffer from increasing depths. In fact, for GNNs, the optimum depth is usually 2 to 5 layers, and then for transformer, the vanilla BERT is like 12 layers. So nonetheless, they are all relatively shallow compared to convolutional neural networks like ResNet. And then the shallowness has been seen like as one of the major challenge for developing more powerful GNNs. So this is because all of them suffer from this phenomenon called oversmoothing, which refers to the phenomenon that increasing model depths leads to homogeneous node or token representations. So here in the bottom is a visualization of the output of a 5-layer graph convolutional network, where we see that as we increase the nodal depth from 1 to 5, the node representation starts to converge to the same representation vector. So people are curious about what is the underlying mechanism leads to this phenomena. What has been understood in the literature is the simplest case, where we have symmetric graph convolutional networks with the activation function being ReLU and leaky ReLU. And in that case, people prove that this type of architecture loses expressive power exponentially, meaning that because oversmoothing happens exponentially fast in that case. And then the intuition in the graph convolutional case is actually quite simple. One can think of what graph convolution does to each node at each layer is that it updates the root node's representation with the average of its neighboring node. And this operation smoothes the node representation over the entire graph. And if one applies too many rounds of this operation, every node converges to the same representation vector. On the other hand, attention was introduced precisely because people want to distinguish different neighboring nodes when doing the update and only do the update with the important neighbors. So the natural question is, can attention prevent oversmoothing? So this is actually a long-standing open question in the theoretical GNN literature, and then people have not reached consensus yet. On the one hand, some people believe that attention can learn the appropriate or right aggregation function to fundamentally prevent or elevate oversmoothing. But on the other hand, people empirically observe that oversmoothing seems also inevitable in attention-based GNNs, such as graph attention network, GAT, or transformers. So the spoiler of our work is that in this work, we provide a definitive negative answer to this long-standing debate in the literature. And then the second question we answer in this work is, what is the role of nonlinearities on oversmoothing? Can we conclude about a general class of nonlinearities instead of the specific instances of ReLU and leaky ReLU? Because they're quite special as well, because say like they're homogeneous. So here's the summary of our main result. And then the punchline is attention-based GNNs under general nonlinearities also lose representation exponentially because oversmoothing happens exponentially in this type of architecture. And we have very minimal assumptions, meaning that our result is able to account for a wide range class of attention-based GNNs, including popular architectures such as GAT and different variants of GAT and transformers and graph transformers. And we also have very minimal assumptions on the nonlinearities, so our analysis is able to account for a wide range of commonly used nonlinearities such as ReLU, leaky ReLU, TH, ELU, and even non-monotone ones like GLU or CLU. Moreover, our analysis reveals that even though oversmoothing happens exponentially in both graph convolutional networks and attention-based GNNs, the rate in the latter is actually potentially slower. And also the specific rate depends on which nonlinearities one uses. So let's dive into the mathematical analysis. So by graph attention, what I mean is that given a node representation vector hi and j, we first use the attention function phi to calculate a row attention score between them, eij, and then we perform mass normalized attention based on the graph structure, meaning that for each node I only do the softmax operation with its neighboring nodes. And once we calculate the attention score between node I and j, we have a row stochastic matrix Pij representing the aggregation step. And then the layer-wide update of an attention-based GNN could be written in the bottom form, where the output of the t+1th layer is the product of the aggregation matrix PT times the input of the t+1th layer xt times the weight of that layer, and then the product is passed through the element-wise nonlinearity sigma. And then to measure oversmoothing and define oversmoothing, we need a definition for node similarity. And then
so a no similarity measure is defined to be the case such that it satisfies the condition where it equals to 0 if and only if all nodes have the same representation vector. And then oversmoothing is defined to be the case where this no similarity mu converges to 0 exponentially fast. And then in this work, we use the following no similarity measure, which is basically the norm of the distance from the no representation matrix to the all-one space. But our result generalized to any Lipschitz no similarity measure, including the popular ones used in the literature, which is the physics-inspired one called graph Dirichlet energy. But this one is easier to work with in the proof. And then the assumption we adopt in the, like I said earlier, is quite minimum, is that, so we just require the graph to be connected and non-bipartite, and then the attention function phi to output bounded attention score for a bounded input, and then the weights to be to behave under some regularity condition, and then finally the nonlinearity to satisfy some minimum assumptions. So say if your nonlinearity is 1 Lipschitz and has 0 as a fixed point, then it automatically satisfies our assumption 4. So the way we do our analysis is that we abstract our attention-based GNs as a time-varying dynamical system. So recall the layer-wise update rule. If the activation function is the identity map, then the output of a T+1 layer attention graph neural networks will look like this product, where you have T+1 aggregation matrices times the input to the neural network X times T+1 weight matrices. And then one thing I want to highlight is that due to attention, all the aggregation matrices are different for different layers. And this is one of the main difficulties in analyzing attention-based architecture. Because previously for graph convolution, because each aggregation matrix is fixed, so you can just do a spectral analysis and then get the exponential convergence result. But here, because different aggregation matrices are different, so that proof technique just doesn't work anymore. But before I let you know how we do the analysis for the product of inhomogeneous aggregation matrix, let's first deal with nonlinearities. So we make use of the following trick that the application of element-wise nonlinearities to a vector could be written as a diagonal matrix times that original vector. So the ith column of the node representation matrix X plus 1 could be written as a weighted product of the matrix D representing the nonlinearities and then P's representing the aggregation matrices. And then it follows from our assumptions on the nonlinearities that the diagonal entries of all the diagonal matrices representing the nonlinearities will be between 0 and 1. And then using that abstraction or formulation of our GNs, we prove that under our assumptions, the graph attention cannot fundamentally change the connectivity pattern of the graph in the sense that all the aggregation matrices in different layers, even though they are different, they would have the same sparsity connectivity pattern as the original graph. And then this result might look a little bit weak at the first glance, but this is actually the key result, actually leads to the exponential convergence. And then because in the definition of oversmoothing, we're interested in the behavior of the node representation matrix X, and we're interested in its asymptotic behavior as the number of layers goes to infinity. So because we look at this problem from the perspective of dynamical system, essentially we're interested in like, what is the ergodicity behavior of this underlying dynamical system? So here in this work, we define ergodicity of a dynamical system to be as follows, where it is ergodic as long as the product of the matrices converge to the case where all rows within the node representations are equivalent. And recall that the node, the trajectories of the node embeddings can be written as a weighted sum of products of the matrices D's and P's. And then if we define the family for those matrices as MG epsilon, then any sequence from that family would be ergodic, meaning that any infinite product of matrices from these families, these P would converge to the case where all rows are equivalent to the other, meaning that over-smoothing would happen, except we don't know what the rate would be. And then to quantify the convergence rate, and that is actually very important because in the definition of over-smoothing, we want the convergence to be exponential. We need to make use of another important concept called joint spectral radius, which is a generalization of spectral radius to for a single matrix to a family of matrices. So basically, joint spectral radius measures the maximum growth for a product of matrices. And for our family of matrices D's and P's, if we project them into the space perpendicular to the O1 space, and then we have the projected family of matrices, we can actually show that with the previous lemma, where because the attention cannot fundamentally change the connectivity pattern of the graph, it will actually lead to the following result, where the joint spectral radius of this projected family to be strictly less than 1. And then based on the definition of joint spectral radius, and also the definition of the node similarity measure mu, we conclude that because the joint spectral radius is less than 1, mu will converge to 0 exponentially. And then the intuition is because mu converges to 0, meaning that everything converges to the space spanned by O1, and then joint spectral radius measures how much the projection into the space perpendicular to O1 vanishes. And then because it's strictly less than 0, it vanishes exponentially fast. And that's why we have over-smoothing at the exponential rate for attention-based GNs. And then something I want to remark is that even though joint spectral radius is a very interesting and useful concept for the proof, it is actually NP hard to calculate in practice, even for 2 matrices, and NP hard to approximate, I believe, under most circumstances. But even though it is hard to compute the exact joint spectral radius, it is actually straightforward to lower bounded just from the definition. So if we let lambda to be the second largest eigenvalue of the symmetric graph convolution or symmetric random walk matrix of the underlying graph, then it holds that this second largest eigenvalue will be would be smaller or less to the joint spectral radius. And then from the previous literature, we know that this lambda is the exponential convergence rate for the graph convolution. So even though attention-based GNs and graph convolution both over-smooth exponentially, it is natural to expect that attention-based GNs to potentially have better express power at a finite depth because the upper bound is looser. So we verify our finding empirically, where the first row shows the change of the node similarity measure mu with respect to different number of layers. And then the first row is for attention-based GNs, and the second row is for graph convolutions. And we see that even though both cases we have exponential over-smoothing, but indeed for attention-based GNs, this actually happens slower. And then the same result holds for heterophilic graph as well. And because our theory is developed for generic graphs, so it holds for any kinds of graphs, and which can be neither of them. And then a second thing I want to mention that I find very interesting is that because we know the convergence rate depends on the joint spectral radius of the family of matrices D and P, and D depends on which specific nonlinearity function you choose. So, and here different colors represent different kinds of nonlinearities, and we see that actually some type of nonlinearities actually have an edge over different other type of nonlinearities in the finite depth case. So one lesson we learned from analysis is that even though ReLU is the default choice people would use for graph neural networks, is probably not the best in terms of over-smoothing. And before one resort to some very dramatic way to come back over-smoothing, maybe the first step one might want to try is to just switch nonlinearities and your graph neural network would just be better in that case. So here concludes my talk. In summary, we have answered two fundamental over questions about over-smoothing in attention-based graph neural networks, including transformers. For the first question, can attention prevent over-smoothing? The answer is no, because graph attention cannot fundamentally change the graph structure, which in fact results in over-smoothing at an exponential rate. Second, what is the role of nonlinearities on over-smoothing? There's nothing special about ReLU or leaky ReLU. Over-smoothing is guaranteed to happen exponentially for a wide range of nonlinearities. And then the specific rates would depend on which nonlinearities one choose. So more details can be found in our paper, and thank you for your attention.
Hello? Yeah. So due to the time limit, we also will not take questions at this point, and I believe Xin is happy to answer your questions offline and have more conversations with you. So our third contributor talk is actually one of our own. Han Chen just graduated from the ECE department of Johns Hopkins. He's going to talk about early neural alignment in two-layer ReLU networks with small initializations. And also I want to announce a small change to the schedule. We'll have a 15 minutes break so that you can stretch your legs after this. So go ahead, Han Chen.
Hi, good afternoon, everyone. I'm Han Chen Min from now University of Pennsylvania. Today I will talk about some of our recent results about neural alignment in two-layer ReLU network. This is a joint work with Enrique Machada and Binu Vidal. Okay, so ever since deep learning has gained great access and gained great success in many application domains, and we theorists have been trying to thinking about how we should understand the magic behind it. So here in particular, I am showing you two key questions that people have been raised in this community, and there are a lot of huge efforts to writing papers, thinking about formulations to trying to answer those two questions. One is about convergence, why we can successfully train our neural networks despite whether our loss function is super non-convex. And then the second question is about generalization, why we train our neural networks. It happens to generalize perfect, well, very good on the over unseen data. With those two questions in mind, I want to talk about a few subsets of the recent work that has been trying to tackle those two questions. The first line of work is the neuron tangent kernel analysis, and we heard in the morning sessions, we already talked about how some of those neuron tangent kernel analysis could be useful in understanding graph neural networks. And in particular, this neuron tangent kernel, as I think Luana said, generally, people would consider a network with extremely wide hidden layers, and we have to initialize our weights with Gaussian initialization with some large variance. Okay, and good thing about this NTK analysis is that gradient descent converges exponentially to the global minimum. That's good because that partially answers our first question. But how about the second question? The second question is that why this neural network would generalize well, right? And if you think about how the neural tangent kernel works, it is roughly doing some kernel regressions on our training data with a fixed kernel that is given by this neuron tangent kernel. That's meaning that the underlying representation of our training data is determined by that kernel. But you would agree that for many tasks, there could be much better feature representation of our input data that explores the data structure. If our neural network would be able to learn those features, it will generalize much better. But if we operate the neural networks in the NTK regime, we wouldn't be able to learn those nice features. Okay, so then following that type of things and the alignment, I'm talking about alignment, but the text is not well aligned. But yes, so there's another nice paper saying that we need to get out of this NTK regime. And this nice paper saying that actually you could just do one thing, that is just decrease your initialization scale. Okay, and in this paper they show that in the Lth layer diagonal linear networks, there is some implicit bias with gradient descent, and that regularization is explicitly controlled by your initialization scale. If you have a large scale, then it's kind of like an L2 regularization. But then if you decrease your initialization scale, you actually get some regularization that promotes sparsity. Okay? And then following that type of work, people kind of start, and maybe we should look at more architectures. Specifically, there are some work that studied matrix factorization, and we see that small initialization actually promotes low rankness in our model. And our work will study two-layer radio networks along the same line. Okay, this is a DeepMath conference, but you would probably argue that two-layer is not deep, but at least I will promise you there will be some math. Okay, I will just very quickly pass through this because there is some prior work that has been looking at radio networks under small initialization, and generally what we did is there will be. I warned you that when we're trying to carefully analyze those training dynamics, there will be some assumptions on the data that it resembles what we generally assume like a linear separability. But generally, those notions will be slightly stronger than linear separability. And then there are other requirements either on the hidden layer width or whether those analyses be quantitative or not. And in our work, we'll be kind of relax some of those assumptions and make less requirements on the hidden neurons. Okay, so here is my talk outline. I have to briefly talk about why we care about small initialization, and I have discussed a few prior work. Then I will jump into the problem settings of training a two-layer radio network. Then I will illustrate the training dynamics using a toy example. And from that toy example, what we will see is that the training dynamics consists of two stages. And the first stage will be all about alignment, as title suggested. The second stage will be about fitting the data. Okay, and well, this is a short talk, so I will zoom in to the first stage, and in that stage, I will carefully analyze the neuron dynamics in terms of how those weights are changing following this along the training trajectory. And then I will show our main results and then conclude. Okay, so let's get to the problem settings. We are considering a binary classification problem with some input data xi's, and then those either they have a +1 label or -1 label. For the toy example that I'm going to show you, I will visualize those input data points as orange crosses or blue crosses, depending on whether it is a negative data with -1 label or a positive data with +1 label. And since we are looking at two-layer radio networks, that's our classifier. And then it is parameterized by some WJs, VJs ranging from J from =1 to H. So there are little h hidden neurons. And then in particular, I mostly care about the rows of the first layer weight matrices, which are WJs. And we will carefully analyze how it evolves during training. Okay. Similarly, I will visualize those neurons in those red dots, but because the title suggests we are looking at alignment, in the separate plots, I will plot the direction of the neurons. Okay, so that's a normalized neuron directions. Okay, and I just, because we are looking at the classification task, I just randomly pick classification loss, that's exponential, but logistic loss will do as well. Okay. And the way we train this neural network is we start from small initialization, meaning that we will initialize our weights with random Gaussian initialization, random Gaussian distribution, but with a small variance controlled by epsilon. Then we will run this gradient flow dynamics starting from that initialization. And then by gradient flow dynamics, I mean I continuously update the weights following that ODE. Okay, and then we will analyze the solution to this ODE. Okay, let's just jump into how this gradient flow dynamics works on this toy example. Okay, let me remind you that at initialization, we did a small initialization. So at initialization, all neurons will have small norm, and they are pointing towards random directions. Okay, and if I run this algorithm, what we see that the first stage, during this first stage, the neuron keeps small norm because in the first plot we see that the neuron is still close to the origin, but they are trying to align the directions with the input data you have. Okay, and then we see in this phase we don't even see any decrease in the loss. In the second stage, once the neuron has some good alignment with the data, it will start to grow their norm. And we only in this case, we see the loss start to decrease. Okay? And if I were to summarize what we see in this toy example, I would do the following, is that I will have a plot that show you how the neuron has changed over the entire training trajectories. But instead of looking at the changes in the absolute neuron directions, neuron positions, I will first consider the dynamics of the neuron norms and the dynamics of neuron directions separately. That's exactly what I plotted. I plotted the changes in terms of neuron norm and changes in the neuron directions on the same plot, and you see that there is 2 stages. The first stage, the only actions is happening in terms of the neuron directions, and the second stage is all about neuron growing its norms. Okay, and then hopefully this is kind of like clear that there is a clear separation between 2 stages, and one is about alignment, and the other one is fitting the loss, fitting the data. Okay, and for this talk, I will focus on trying to get more detailed discussions on the first phase. Let's get to the some discussions on this neuron dynamics in the first phase. Okay, so yes, I told you that when I trained this radio networks, I used a gradient flow dynamics that shown here, but hopefully I have convinced you that the real thing we need to look at are the dynamics of the neuron norm and the dynamics of neuron angle directions. Okay, so we should go first from the gradient flow dynamics to the changes in norm and neuron's angular dynamics. Okay, and how should we do that? There is a lot of assumptions. There are some technical assumptions, and we need to assume small initialization scale, but there are extra things, the extra math you need to do. But in the end, once you get through all those math, you will see that going from the gradient flow dynamics, there will be some nice representation on the time derivative of the WJs, given by WJ and VJ in that expression. Okay, and then this expression is nice because the changes in WJ doesn't depend on other neurons. So we can just understand the neurons dynamics individually. Okay, and there is an annoying sign of VJ of 0 at 0 initialization. I will just assume it to be +1 throughout afterwards, but there is a corresponding analysis when that sign is -1. Okay, so let's assume that is +1. So now we get this type of approximation of the time derivative of the neuron WJ. Okay, how should we go to the neuron dynamics? The neuron dynamics is just computed, right? The neuron time derivative of the square root of norm is just the inner product of the neuron's time derivative of neuron times itself. Okay, and we get some neuron norm dynamics that is here. Okay, okay, and never mind. I want to do the laser, but okay, there we go. So there is some inner product terms. We just need to do a Cauchy-Schwarz to upper bound it. And then we get some upper bounds on the time derivative of the square norm, okay? And give myself. So it's kind of like this expression is simply saying that the neural norm can at most grow linearly at this stage, okay? And then we're gonna use that to get a calculation on how long this alignment phase lasts. in terms of the neuron's angular dynamics, what we're gonna do is the same. How we should compute the angular dynamics? We should first normalize the time derivative of Wj by the norm of Wj. And then the second thing we to do is project that vector onto the subspace that is orthogonal to Wj, okay? And then once we do this computation, we get some approximation of the neuron's angular dynamics that is shown here, okay? With those two, we can get more detailed explanations for what we see on this table about the alignment phase, right? So because we observe that the changes in norm, the neural norms, is very small at the initial stage. But this is already telling you that, right? At initialization, because I initialize normal the Wj on the small initialization, this norm is small. So automatically, the time derivative of the square norm is also small, okay? But because the square norm has a linear growth, this type of upper bound can only be held for a set amount of time. That is determined by the initialization scale, okay? And then for the neural angular dynamics, there's just we will see how it works, visualize how it works. But essentially, if I were to summarize this equation in one sentence, it's just the neuron moves their directions towards a centroid, where this centroid XA is computed based on my current neuron's position, and it's just a sum weighted combination of my input data. The weights is given by the label, okay? And how this neuron's angular dynamics works, because, well, in the first stage, we care about most about the directions. Let's pretend first the XA, the centroid, is fixed. What I'm gonna do, when I try to compute the time derivative of the neuron directions, I just project that XA onto the orthogonal subspace and to the Wj. So this time derivative is pushing my neuron towards XA. So that is how, in general, this will work. But what makes this things a little bit tricky is the XA depends on my neuron current position, okay? So as my neuron move on the unit circle, neuron direction moves on the unit circle, the XA changes. Every time the neuron sees a new data points or lose one of the other data points, the XA changes. I have to recompute it. So essentially, the neuron is not chasing a fixed target, but a moving target, okay? And I call that type of behavior early alignment, because neuron could start off at any directions on the unit sphere, and it only see a subset of data, and then this XA is computed based on that. But as the neuron is moving towards that XAs, it sees different set of data, and then this XA is changing, okay? And I call that type of phase early alignment. There has to be some time it stops, meaning that there is some nice configuration for the neuron. Once it sees a good amount of all the positive data and none of the negative data, you see that now this centroid no longer moves. So this neuron will get pushed towards the centroid. And when we look carefully what this centroid is computed, it is precisely pointing towards the positive data set, okay? And I call that phase where the neuron is trying to get further close to some positive data center as refined alignment, because this happens after the neuron gets some good alignment during the previous early alignment stage, okay? And probably, I don't know how much time I got. Okay, yes, so hopefully, let me try to summarize what I said here is that what I essentially showed you is that after breaking down, after carefully looking at the neuron dynamics here, I showed you that this alignment should be further decomposed into two phases, where there is an early alignment phase, there is a refined alignment phase. Why we need to do that is essentially the technicalities behind analyzing those phases are actually different, because whether either the centroid is moving or fixed is totally different things, okay? And then so there is another split. our first theorem says that if the data is somehow well separated and measured by some constant positive number mu, then this early alignment phase will last at most log of n over square root of mu times. So we provide upper bounds on the time the neuron needed to achieve some good alignment with the data. Okay, and then actually once the early alignment is achieved, that is sufficient for the final convergence. So that is sufficient for the loss to decrease to the global to decrease to zero. Okay, and then there are some extra results that are about refined alignment. That the technical things behind that type of results is already existing in the prior work. I'm gonna skip. And I'm gonna skip that as well. So, but I hopefully this slide's already summarized what I have talked to you about, and it's just there are two stages. One about alignment, the other one is fitting, and then I showed you that the alignment can be further broken down to two, and then we provide the quantitative bounds on how long those two phases would last. And the future work would be, because actually, if you check our paper, there are some underlying strong assumptions on how the data should be well separated. We should probably, there could be a way to relax those assumptions. And then, of course, next time, maybe the next deep math, I would go deep neural network so that it's a really deep math. Okay, thank you.
Thank you, Hanchen, for the great talk. As mentioned, we will have a 15 minutes break. So in this time, we'll have a coffee and also snacks in the back. So enjoy yourselves. But before you go, I have two announcements. One is like at 5 p.m., we'll have post session in the other room where you have breakfast and lunch, like the Great Hall. So I'll see you there. And the second announcement is like if you get a travel award, please talk to Cindy in the back, who will tell you how to fill those forms to get reimbursed. Okay, now enjoy yourselves, and let's come back at 3:45. Thanks. Hello. Please be seated, and we're going to have our last talk before the post session this afternoon. It's my great pleasure to introduce Tom. Tom is Volpe Kupal, endowed professor of computer science in the University of Maryland. His research lies in the intersection of machine learning and optimization and targets applications in computer vision and signal processing. Today, he's going to talk about an empirical perspective on generalization. Tom, the floor is yours. Thanks.
All right, great. All right, so sound is good. Can you guys see my slides projected okay? We're good? All right, thank you very much. All right, so this talk is called An Empirical Look at Generalization. I'm gonna do something a little bit different. This is the DeepMath conference. We're supposed to talk deeply about math. I'm going to do something very controversial here. I'm not going to talk about math. I'm going to talk about something we all hate, hacky, hand-wavy experiments. All right? So just to prepare you for this talk a little bit, here's the nutrition facts for this talk. For you international travelers, the FDA requires us to put nutrition facts on everything, so here you go. This talk, you will get 0% of your daily value of math. So don't expect any math. But you will get 100% of your daily value of pictures. I'm going to show a lot of pictures, and I'm hoping that you get at least a little bit of intuition out of this talk. So why am I not going to talk about math? Here's why I'm not going to talk about math. A lot of folks are very interested in questions like, can you get generalization bounds for neural networks? And this is something a lot of people work on, but the answer is yes, you can get great generalization bounds for neural networks. Here's a generalization bound for neural networks. Consider a deep neural network. It satisfies some assumptions, irrelevant, some assumptions. If it has d parameters and n data points, then I can put a really nice bound between the training and the test error that decays towards 0 as the number of data go to infinity. There we go, generalization bounds for deep neural networks, right? So they exist. But then what are the assumptions? You got to kind of wonder what are the assumptions. Well, in this case, I'm assuming that it's a one linear layer neural network with more data than it has parameters. Okay, so that's doesn't seem particularly interesting, right? And so what we might do is criticize a result like this because superficially, this system doesn't feel like it is a neural network. Neural networks are supposed to have multiple layers, right? And so we can come up with other generalization bounds that describe models that superficially look like a neural network. For example, you might have like a multi-layer system, but then you might also make very strong restricting assumptions that allow you to reduce the question of generalization to something like standard parameter counting methods, to something like model compression. And the point is just that having that superficial similarity, describing a model problem that looks like a neural network in a superficial way, doesn't necessarily mean that the math that you are writing down actually describes the underlying phenomena that are responsible for what I would call strong generalization. So the generalization phenomena allows neural networks to do so much better than classical models. And so I think that there's a bit of a disconnect between the machine learning world is sort of ripped into two pieces. And there's two groups in here. You have people that work on fundamental theory, and then you have people that work on engineering science. And they're doing all sorts of scientific experiments. Some people would say, well, aren't the theorists doing science too? In my definition of science, you make a hypothesis and you do an experiment, and then you look at the outcome and you gain knowledge from the world by doing experiments, right? So you have engineering science, and these are the people they're doing all the hackery, trying to get the MAP score on COCO as high as they can in various ways. And then you've got fundamental theorists that think about math all day, and we write down generalization bounds, but it's not always clear whether or not those bounds are appealing to the actual phenomena that are important for deep neural networks. And then I like to think that there's a space in the middle of people that do fundamental science. So science, but the goal of these experiments is not to get a 0.1% better score on COCO. Our goal here is to do scientific experiments that really tell us something about the way that deep neural networks work. And without doing that science, I don't think it's possible to know whether the theory that we're writing down is correct. because deep neural networks, there's all sorts of reasons they could generalize. But at the end of the day, they seem to be exploiting particular properties of data sets that we can't really know unless we're willing to do the science and actually look at those data sets and look at the properties and understand what's going on. And maybe doing fundamental science will give us a better sense of what kind of theoretical results are missing and what kind of theoretical results we have that are actually meaningful. Okay, so this talk, I'm going to show you a few hacky, hand-wavy experiments broken into two parts. The first part, I'm going to talk about the origins of implicit regularization and some experimental evidence that tells us some things about where that might be coming from. And then in part two, I'm going to talk about a completely different kind of generalization than we usually think about. I'm going to say some things about whether neural nets can exhibit logical extrapolation, which is the ability for them to solve harder problems than they were trained on. So we'll start here with part one. So I'm going to ask this as a scientific question. What is it, the original? I said, what is the origin of implicit regularization? And there's a pretty mainstream answer to this question. I think that many people feel that it is what people say the implicit bias of stochastic gradient descent. There's alternative theories out there, but I think this is a fairly mainstream one. People believe that that the optimizer is responsible for generalization. And I think one of the reasons people believe this is because theorists look at what's going on in the empirical world, and we see that all of these people that are fighting against each other to get incrementally better scores on benchmark data sets are using stochastic gradient descent. If they use something like Atom, then their results go down by 0.3%, and it's a disaster. And so as theorists, we must conclude that the reason why deep learning works is because of stochastic gradient descent. Right? But I think we might be overfitting a little bit to what we're seeing. I have a crazy alternative theory, which is that most of generalization can probably be explained by loss landscape geometry. And I don't think most people believe this, but I'm going to present some evidence, and I'm going to try to convince you that empirical evidence doesn't really strongly support this mainstream theory, but it does seem to indicate that the crazy alternative theory of loss landscape geometry might not be so crazy. At least I hope to convince you of that. If I fail, I'll just convince you that I'm crazy, and I guess I'm okay with that too. Okay, so let's start with I call this a picture of generalization. Why is it that people think that the optimizer is so important for generalization? So this is an example. I'm going to take this is a two-way classification problem. It's the Swiss roll. I'm going to train a neural network with 10,000 parameters or so. I'm going to start at some random location in parameter space. I'm going to run the optimizer, and when I run SGD, I get all of these iterates. So we carve out this trajectory in parameter space, and then stochastic gradient descent ends at a good minimum that gets 98.5% test accuracy. So that's pretty good. Now what I'm going to do is I'm going to start at each one of these SGD iterates along the way, and I'm going to run a special optimizer that finds bad minima, and I get all of these minima. So these are bad in the sense that they minimize the training loss. So they get training loss just as low as the good minimum, but none of them can do any better than 53% accuracy. This is a two-class problem, so none of them are really doing substantially better than a coin flip, right? So they're all pretty bad. So you look at this, you can look at this result and you can say, well, something is going on here, right? When you run this stochastic optimizer, it passes through this minefield of bad minima, and somehow it plucks out this good minima at the end, and it just misses all of these bad minima along the way. And I think that the intuition here is that somehow the optimizer knows what it's doing. So the optimizer is very smart, and it knows to avoid all of those bad minima and head straight for that good minima at the end. It must be because of the optimizer. But I'm not so convinced that's true. So most people would say that this occurs because of the implicit regularization of stochastic gradient descent. And I think that's a pretty mainstream theory. But when you actually run experiments to try to isolate the effect of the optimizer, it turns out the optimizer doesn't matter as much as you would think. So just starting with the stochastic part in stochastic gradient descent, what happens if you remove stochasticity entirely? So this is an experiment where we're going to train Resin 18 on CFAR10, and I'm going to see what happens if I completely remove stochasticity. So if you take a pretty popular repository from GitHub, it gets about 95.27% if you train Resin 18 on CFAR10. For Resin 18, I think that's considered to be pretty good. We ran a much larger hyperparameter sweep for a very long time, and we managed to boost that up to about 95.70%. And this is with small batches, a batch size of 128. And so one might suspect that if stochastic regularization is so important, you wouldn't be able to do that well if you use full batch gradient descent and there's no stochastic sampling. But actually we can do pretty well. So if we do full batch, so every batch is using all 50,000 samples, there's no stochastic sampling at all. If we do a very elaborate hyperparameter search, and my former postdoc, Jonas Skyping, ran this on our cluster during spare scavenge time for almost a year. But we managed to eke out a performance of 95.91%, which is at least, it's the best result for Resin 18 that I am aware of with no stochastic sampling. If you then take that same recipe, so exact same hyperparameters, we're not going to do any more hyperparameter tuning, and we'll just train a bigger architecture. So this is ResNet 151. We get 96.76 using full batch sampling, which is pretty good. The state-of-the-art result with much larger architectures and all sorts of fancy tricks is a little bit over 97%. So it's, with other architectures, it's possible to do a little bit better than this. But I think this is pretty convincing that small batch factor, right, having that stochastic sampling of data is not a fundamental reason why these neural networks can generalize. So let's just talk about the stochasticity and stochastic gradient descent. There's other studies that have tried using very large batches. There's all of these studies on ImageNet, like training ImageNet in an hour, where they crank the batch size up to 64,000. I would also point out the Llama 2 models were trained with a batch size of 4 million tokens. Right, so very large batch training can still succeed in generalizing. So that's about the stochasticity issue in stochastic gradient descent, but there's also the gradient part of stochastic gradient descent. Is gradient regularization important? And I don't think that's really true either. If you plot train and test accuracies on CFAR10 for a whole bunch of optimizers, some of these are gradient based. There's also things like, some of them are aggressively preconditioned, like LBFGS. ProxProp doesn't really use gradient updates per se. It's an alternating least squares optimizer. It's a pretty unusual optimizer. And all of these get kind of the same thing on CFAR10, and they do better than you would ever expect to do with a classical model. There are small differences between these, but I'm not sure that those differences, these are the kind of differences that practitioners fight over because they have to get state-of-the-art results for CVPR. As theorists, I'm not sure that we should care about these small fluctuations. Okay, so the alternative hypothesis is that maybe the success of deep learning doesn't have so much to do with the bias of the optimizer per se. Maybe it has more to do with the properties of the loss landscape. Okay, so in order to say something about the properties, the geometry of good minima versus bad minima, we need a way to find bad minima. And the optimizers that we typically use have this very strong tendency to find good minima. So you got to have a way to find bad minima if you want to be able to investigate how they're different. And so we'll do that using poisoning. So I'm going to take a classification problem. You've got two classes, the blue and the green, and you hope to get a nice decision boundary like this dotted line. And the way you usually get that is you train a neural network by minimizing something like a cross entropy loss. What I'm going to do is I'm going to take this training set and I'm going to drop in a whole bunch of extra data points. These are held out data points. And I call this the poisoned data. And I'm going to cook up a loss function that contains the cross entropy on the original data and the reverse cross entropy on the poison data. Reverse cross entropy is low when you've gotten everything wrong, and it's high when you get everything right. So I'm going to minimize both of these together, and I'll find a classifier that aces the train set. So it minimizes the cross entropy loss on the train set, but it squiggles all over the place, and it completely fails to generalize. And we'll do that by poisoning the classifier with holdout data and this reverse cross entropy loss. And that allows us to find, and then after we train this, we can throw away the holdout data and we get a decision boundary that gets a perfect score, gets effectively 0 cross entropy loss on the training set, but it generalizes poorly. And that's how we found those bad minima in that example that I showed, where we had all the bad minima off the side of SGD. So now we have a tool to find bad minima. You can ask a question like, what's the difference between good and bad minima? And we can find them, and we can make pictures of them, and we can look at them and see if there's a difference. So one way that they're different, the good minima and bad minima, has to do with their sharpness. And I think that the theory world is pretty severely divided between you have flatness believers and then you have flatness disbelievers. I'm a flatness believer. There are a lot of papers out there written by flatness believers. There are also papers that really focus on this issue that if you use sort of a trivial definition of flatness, you don't normalize parameters in the correct way, what I would consider the correct way, you can come up with definitions of flatness and sharpness that don't correlate well with generalization. And I'm not going to do a deep dive on the differences between all these definitions. But in the studies that I'm going to show, we normalize each filter. If we're studying a COMNet, we normalize each filter before we compute the sharpness. So every filter has the same norm. And that removes the kind of invariances that people typically exploit in these papers that claim that sharpness doesn't correlate with generalization. Okay, so what is the intuition behind the flatness hypothesis? This is my very hand-wavy explanation of what's going on. Why is it that flatness is good? There's all these papers that empirically have observed that flatness correlates with generalization, but why? What makes flatness good? So if you think about a classifier, you would hope to find a wide margin. If you got the blue points and the green points, a good classifier should slice right between them, and it should have a wide margin, right? Well, if you have a wide margin, then that should also correspond to a flat point in the loss landscape. And the reason why it should be flat is because if I perturb the parameters, so I grab that parameter vector and I wiggle it around in the loss landscape, because there's a wide margin, when the decision boundaries snake around in input space, they don't cross over the training data points because there's a wide margin, right? If you have a really wide margin, then I can move that parameter vector really far before I start misclassifying data points. And so intuitively, it seems like there's a nice relationship between these things. For something like an SVM, we know how to quantify the margin, but for very complicated nonlinear problems, it's much more difficult. But this concept of flatness is basically an analog of wide margin that you can use for nonlinear classifiers. If you had a very bad classifier, like one of our poison classifiers, this gets perfect score on the train set, but this corresponds to a very sharp minimizer because it doesn't have a wide margin. And if you perturb the parameter vector just a little bit, the loss goes up because the decision boundaries are close to the training data points. You don't have that wiggle room, right? And empirically, we observe that this relationship between wide margin and flatness seems to work out in practice. So these are some of the bad minima. Let's look at the bad minima and good minima we found in this Swiss roll experiment. So this is a good minimum. This is the minimum we found at the end of SGD. And you can see it has a nice wide margin between the two edges of the Swiss roll. And there's this really flat part of the basin right there. You can put it down on a table and it probably wouldn't fall over. It's very flat. But if you look at one of the bad minima, you don't have a wide margin. The decision boundaries sort of squiggle all over the place and come very close to the training data points. And you correspondingly have an extremely sharp basin. And you can find these kind of sharp and flat correlations in other data sets. Here's Street View house number. So here's a flat minima that gets 97% test accuracy. And here's a sharper minima that gets 28%. This is on CFAR 10. So this is a not so good minimum on CFAR 10. It gets 83% accuracy. And you can see there's a blue basin at the bottom here that's not particularly sharp. But if I train a really good architecture like DenseNet, I get a really flat, really wide basin. And this one is also, so you can't see it so well in this figure here, but it's also so flat at the bottom that you could put it down on a table and it wouldn't fall over. Okay, so that's the intuition between sharp versus why flatness is good. And like I said, there's a lot of papers that claim flatness is good and have claimed to observe these sort of correlations. What I'm trying to do here is just give you some intuition for why that might be true. But the question that I'm really interested in is this question: why does generalization happen? Why do we find good minima to begin with? And there's all sorts of possible explanations for this. It seems like you run an optimizer and it always knows to pluck out these wide flat basins and it always knows to avoid these narrow sharp basins. And then the question is, why is that? Is it because there's some magical knowledge that stochastic gradient descent has that other optimizers don't have? A much simpler explanation that I like is that maybe it finds the big wide basins because big things are big. It's easy to find things that are big, right? If you just did a random exploration, you just randomly searched in the loss landscape until you found a minimum, you're more likely to land in one of these wide flat basins just because they have more volume. It's the reason it's easy to find a boulder in a haystack but it's hard to find a needle in a haystack, right? It has to do with the volume. And that volume discrepancy could actually be what explains the apparent implicit bias of optimizers. And it could also be, it's a factor that doesn't depend on which optimizer you choose. And this volume disparity is amplified by the curse of dimensionality, which might be a blessing in this case. You're training these optimizers in very high dimensional spaces. And so you look at these two minima and you might think, well, that sharp one, it's not so much smaller than the wide one. But in a 10 million dimensional space, being just a little bit narrower actually corresponds to a huge difference in volume. And the probability of landing somewhere is proportional to the volume of that region. So I'm going to show you some experiments that try to probe a little bit more deeply into this volume hypothesis. In experiment 1, we're going to measure the volume disparity between good minima and bad minima, and we'll observe that empirically, good minima have a much larger volume than bad minima, and we can actually quantify that volume difference. In experiment 2, which is a very recent experiment that we've done, we're going to try to show that the collective volume of good minima is larger than the collective volume of bad minima, at least for a somewhat toyish problem. So how do we quantify the volume of minima? I'm going to do it in a very hand-wavy way. I'm going to just find minimums, and then I'm going to slice off the loss function at a particular cutoff value. In this case, I'm going to use 0.1. And when I slice it off at 0.1, there's a region around the minimum that I'll call the basin. It's the region around it that still has low loss value. And I'm going to try to compute the volume of these basins. So I'll take one of these basins. It's a set of all points that have loss below that cutoff of 0.1. And I want to compute its volume, and I can do that integration using the Monte Carlo method. If I start at a point in the center of the region, then I can just march out in a random direction. If I march in a random direction, I can see how far I get before the loss rises up to that 0.1 threshold. And I can do that in a bunch of different random directions. If you wanted to integrate and find the volume of an ellipse, what you might do is you might break, and if this was only a two-dimensional space, you might break this up into a bunch of little triangular sections and you'd integrate them all together. And what you find is that the volume of this ellipse is pi over 2 times the expected value of r squared, where r is the distance from the center of the region to the edge. And it turns out this formula has a nice high-dimensional analog where the volume is a constant times the expected value of r to the n. So what we'll do is we'll start in the middle of one of these basins, and we'll take a bunch of slices in completely random directions, and we'll just march along the basin until we hit that 0.1, and then that tells us the radius of the basin in that direction, and then we can compute this expected value over all the different directions, and that allows us to measure the volume. So it's basically just a Monte Carlo integrator for measuring the volume. If we do this with the Street View house number data set, on the bottom here we have generalization gap, so we have good minima on the left, we have bad minima on the right, and on the y-axis we're plotting the volume that we computed, and this is the log volume. This is log base 10, and so we find that if you look at the difference between these good minima and these bad minima, there's a volume discrepancy of about 80,000 orders of magnitude between them. So the good minima are a lot bigger than the bad minima, right? These good minima, because of the curse of dimensionality, they're about 80,000 orders of magnitude bigger than the bad minima, right? So if you're hoping to find one of these bad minima, it's going to be tough, right? If you just close your eyes and you treat the loss landscape like a dartboard, so you close your eyes and you just throw a dart, how much more likely are you to hit a good minima than a bad minima, right? It doesn't really matter how intelligent your optimizer is, you're just more likely to land in things that are 80,000 orders of magnitude bigger than the things that are smaller. Yeah. That's a great question, and that's what I'm going to talk about now. So when we came out with this experiment, we submitted a paper on this that will never get into any conference. And one of the nitpicky, not so nitpicky, it's a good point. One of the issues that the reviewers always raise is, okay, this shows that individual minima are either small or large, right? But there could be very, very, very many bad minima compared to the number of good minima. And so this experiment doesn't mean that the collective volume of the bad minima is small. What if there's 80,000 orders of magnitude more bad minima than good minima, right? And for a while, I didn't think that we had any experimental way to examine this question. I was kind of stumped, and my student Pingye came up with a very clever experiment that worked out better than I thought it would. And so he created something that he calls the guess and check optimizer. Here's how the guess and check optimizer works. The guess and check optimizer, it's an optimizer that has no gradient bias at all. And we know exactly what its biases are. So suppose that I have a loss function. It's got some basins, some of them are sharp, some of them are flat. And I'm going to define a loss threshold. That's the dotted line. So maybe it's 0.1. So here's how the guess and check optimizer works. I'm going to randomly guess a parameter vector for my neural network. Just randomly generate it. And then I'm going to check whether the loss is low. And if it is, then I stop. So if it's below the threshold, then I stop. If it isn't low, then I'm going to start over and I'm going to generate a completely different random vector. So I generate a completely different random vector. And then I check whether the loss is low, and it's not. So I sample again and I check, and this does have a low enough loss. And so we say that we've minimized the loss and we terminate. So what is interesting about the guess and check optimizer? The guess and check optimizer, the only bias that it has is from the volume hypothesis, right? The probability of landing in any particular region is exactly proportional to its volume. And so the only bias that this has is from the volume hypothesis. If it were the case that the collective volume of bad minima was larger than good minima, then you would expect this optimizer to fail to generalize most of the time. So what's interesting, obviously this guess and check optimizer is a very bad optimizer, right? This is a very slow optimizer, but you can actually solve various kinds of problems. So this is an example on MNIST. This is a 32-shot problem. We can't train on the entire data set, but you can do a 32-shot problem. And you can compare stochastic gradient descent to guess and check. And stochastic gradient descent does a little bit better. Guess and check gets 93%. Stochastic gradient descent gets 94%. But it turns out almost all of the generalization that we observe can actually be explained by the volume hypothesis. Yeah?
What is a 32-shot?
Each class has 32 images. And the way we train this, we just guess and check until we interpolate all 32 images. And that takes a very long time. But here SGD does do a little bit better than guess and check. But if you think that difference is significant, you consider the fact that when we do this on CFAR 10, this is a 24-shot problem because that's the biggest we can get our computers to handle. Guess and check actually does a little bit better than stochastic gradient descent. And there's some variance here. Obviously, it depends how long you want to run this for. But it's just interesting that at least for these few-shot problems, and that's the biggest thing that we can approach computationally. I'd like to have more large-scale experiment. But at least to probe this issue with these few-shot problems, the volume hypothesis is enough to explain seemingly all of the generalization that we observe when we train a neural network. Yeah.
I'm wondering, how do you generate like this random guess? Because I'm thinking if you generate, like, for example, using random Gaussian, you actually do have some like implicit structure. For example, in high dimension, it lies in a unit circle, right? So you do have some certain type of implicit bias in this case.
Yeah. So we actually choose the parameters uniformly over a sphere. And we, in the appendix of this paper, we actually try that with different size spheres. One of our reviewers was concerned that it might depend a lot on the radius of the sphere, and it turns out it doesn't really depend so much on the radius of the sphere. And that's because if you take your parameters and you blow them up, so you make your parameters bigger, what generally happens is your neural network becomes more confident, but it doesn't actually necessarily change the label that you assign to images.
But I mean, if you generate it on like a sphere, you actually have some, for example, a rotation invariant of your parameters, I guess. Like how do you kind of exclude this from, this property being useful for generalization?
I'll point out that we do also do experiments where we uniformly sample them from a coordinate-wise uniform distribution, and then we still get similar results. I'm not exactly sure what you mean by the invariance on the sphere. Why is that advantageous for generalization?
Actually, I don't know. I'm just pointing out if you just uniformly generate your weights from a sphere, you can just rotate. It's still like uniformly on the sphere. And if you have
that's true. There is a ReLU, and this network does. It's actually Linnet, and it does have nonlinearity in it. Actually, forget if we use the ReLU Linnet or the sigmoid Linnet, but there is a nonlinearity that sort of breaks that rotational symmetry.
I see. Thanks.
Yeah. Okay. so that's part one of the talk. I'm talking a little bit about experiments on the origins of generalization. And part two, I'm going to change gears a little bit, and I'm going to talk about this question. It's like a different, I think a different type of generalization that I find to be really interesting. The question is, can neural nets exhibit logical extrapolation? What do I mean by that? Okay, so humans are thought to have two kinds of thinking. They have fast thinking, which is sometimes called type 1 thinking. And those are tasks that we generally associate with pattern recognition. So you see a dog and you say that's a dog. Then we have type 2 thinking or slow thinking, and this is something that is more of a temporal process. So something like mathematical reasoning. I think it's generally thought that machines are better than humans at type 1 thinking. If you pair machines against humans at something like object detection, machines will generally win, right? But we think that humans are much better than machines at type 2 thinking. And in particular, we're better at logical extrapolation. And so what do I mean by logical extrapolation? If you have a math student, you can teach them to prove easy things. You can have them read a textbook and do the exercises in the textbook. And then hopefully, if they're a talented mathematician, you can give them a harder problem than they have solved before, and they can solve it, but they're going to have to exert more cognitive effort. So they're going to have to think for longer in order to do it. And this gives humans the ability to, we can solve complicated math problems. We can learn with very low sample complexity. So as an example, a professional human chess player has played tens of thousands of chess games in their entire life, but a state-of-the-art chess system that would be competitive with a top professional chess player has actually seen billions of chess games. And one of the reasons why we have such low sample complexity is because we can extract lessons that we've learned from our experiences, and then we can piece those lessons to formulate more complex strategies if we have a long enough thought budget, right? That's an example of logical extrapolation. So I want to ask this question. Can neural networks exhibit logical extrapolation? I would like to build a neural network that can solve harder problems than it was trained on by exerting more cognitive effort. And the way that humans do this, at least this is in a traditional computational theory of mind, we like to think of the human brain as having what's called working memory, and we represent a problem in working memory, and then we have this thing called the central executive, which is in some abstract model of the mind. It's all the machinery that works on that working memory, and it crunches on the working memory over time, and if you give it a long enough amount of time, it can solve very difficult problems. And so what I want to do is build a neural network that has some sort of analogous mechanism, at least from a bird's eye view, that is capable of exhibiting a temporal process that I think is in some way analogous to human thinking. And so the way we'll do that is just with a recurrent net. So I'm going to train on, we're going to start by looking at mazes. I'm going to train a neural network on easy mazes, and I'm going to train a recurrent network. The reason that recurrence is important is because a recurrent network, you can run it as long as you want and give it as much cognitive effort as it needs to exert, and it can try to solve a problem by thinking really hard, right? And then we're going to test it on very hard problems. So at training time, I'm going to let it think for 30 iterations. I'll let the recurrent unit run 30 iterations. At test time, I'll give it much harder problems, but I'll let the recurrent run for, say, 3,000 iterations or 30,000 iterations, and then see whether it can figure out how to solve a hard problem if you just let it think for a really long time. Okay, so step one, if we want to move along this pathway here, is we need to replace the feed-forward computation in a neural network with recurrent computation. That's pretty easy. So a standard neural network like Resident 18 has unique layers, A, B, C, D, E, and then some sort of classifier at the end. And standard neural networks that are feed-forward networks, they're limited in the difficulty of problems they can solve. Resident 18 can only do 18 sequential things. If you have a problem that requires more than 18 sequential operations to solve, then Resident 18 can never solve it. It doesn't matter how much you train, it cannot solve that problem. So I can replace that feed-forward model with recurrent architecture. So I'll have a feature extractor layer A, and then B, 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 just repeat the same layer over and over again. And then at the end, I'll have an extractor that tries to pull the solution out of the memory space. All right, so that's the architecture. And then we're going to train this on easy problems, and then we're going to crank up the hardness at test time and see whether these architectures can solve the harder problems if you let them think for a really long time. So here's what I'm going to do. I'm going to train on procedurally generated mazes. I'm I'm going to train on mazes that are all 9 by 9. So this is an example of what they look like. The neural network will take in the maze, and there's a green dot and a red dot. That's the start and the end point that it needs to start at and end at. And then the label that I'm going to give the neural network during training is just a segmentation map that tells you what the path is through the maze. So the neural network is trained to look at mazes and then reproduce these paths through the maze. And we're only going to train it on 9 by 9. That is all we're going to train it on. And then at test time, I'm going to give it 13 by 13 mazes. So those mazes are harder. So if I have a recurrent network, if I have a feed-forward network, then the performance I get on the training task is 100%. On the testing task, I get a little bit over 25%. That's the horizontal dotted line. That's a feed-forward network. So it can solve some of these hard problems, but not very many of them. If you have a recurrent network, then its accuracy depends on how long you let it think for. So if we let it run for more iterations, the accuracy starts to go up, and it continues to go up once we get outside the training regime. So we only train this on 30 iterations. If you let it think for longer than that, it actually solves a higher percentage of these problems. But then if you let it think for too long, it actually overthinks and the performance crashes, and you can never do any better than that. But we published a paper on this, that you can solve 80% of 13 by 13 mazes with a neural network. I thought that was cool, but I don't think many other people agreed with me. And so then we started looking at this problem and trying to figure out how we could get more impressive performance out of these kinds of things. And it turns out the architecture of the system matters a lot. So we started by taking a feed-forward architecture and we replaced it with a recurrent architecture. But it turns out that's not good enough, because what happens with the recurrent architecture is that every time it reads from the memory and makes modifications to the memory and writes back to the memory, it messes up the memory a little bit. It's like making a copy of a copy of a copy of a copy. And especially because SGD is such a poor and noisy optimizer, you're never going to write back a perfect representation to memory space. And so what we did is we took this recurrent network and we added these skip connections that we call recall connections. It's just a skip connection from the input to of the network into the beginning of every recurrence. So every time you do a recurrent call, the network gets to see its current memory state, and it gets to see a copy of the original features extracted from the original problem that you're solving. And this prevents the network from being able to forget important stuff. If the memory state gets corrupted, it can look back in history and it can figure out what it's missing, and it can regenerate things that it's lost. And so if you run this experiment with the 13 by 13 mazes, now instead of overthinking and falling back down, which is the green line, its performance just keeps increasing as you let it run for longer, and then it hits 100% and it just stays there forever. It never wants to fall back down. All right, so we got that to work on 13 by 13 mazes, and then we said, wonder how much you can scale these things up. So we did an experiment where we train on 9 by 9 mazes, and then we test, this is with 30 iterations. So you train with 30 iterations, and then we're going to test on 201 by 201 mazes, but we're going to give it 2,400 iterations. So you give it about 100 times as much compute at test time than you gave it at train time. And it was able to solve this problem. It solves all of the problem instances at this size. And so I went to my student, he thought this was big enough, and I went to him and I said, bigger is always better. I want to see what is the biggest problem that this neural network can solve. And so this is the biggest maze that it can solve. There's a green dot here and a red dot over here. The reason this is the biggest problem is not because the neural network fails, it's because it's the biggest maze that actually fits in the GPU memory. This is an 801 by 801 maze. And so there's the start point. Oh, I don't know if you can see that. There's a start point and the end point. Here we go. But if you let the network crunch for long enough, it'll generate this solution path. And producing that solution path takes about 20,000 thoughts. So it has to iterate for 20,000 iterations, and that corresponds to about a little over 100,000 convolution layers. It's about 100,000 convops to solve this problem. Right? But this was only trained on 9 by 9 mazes, and it never did more than 30 iterations at training time, but it is able to solve this problem with 20,000 iterations of test time. Okay, so one of the questions we started to ask is, what kind of algorithm is this learning? It seems like it's learning an algorithm. I wondered if it was interpretable. And so we did these visualizations. You just run the solver, and then you extract the solution from the memory state after every recurrence. And you can actually see what's going on. It turns out that it's using a classical parallel algorithm called dead-end filling. which was both exciting and unexciting to me. I was excited that it was rediscovering a classical algorithm that's analogous to what a human would discover. But I was also a little disappointed because I was hoping it would do some really weird, cool, uninterpretable stuff like neural networks do sometimes. But it turns out it does both interpretable things and uninterpretable things. So the default solver that it uses is dead-end filling. But if you let it solve the maze halfway and then you add a huge amount of noise to its memory space, we're just going to add a gigantic Gaussian perturbation to its memory space. When you extract the solution, it looks like this, so you just get garbage. But if you do this, it actually stops solving for a while and it repairs its memory space, and then it will regenerate a correct solution to the problem. So it has some sort of error correcting ability. It'll generate the solution to the problem. If you then let it solve the problem, but then you change the starting and the endpoint, so we change the starting and the endpoint of the maze, and we let it keep running from its current memory state, then it will actually regenerate the new solution much more quickly than if you let it solve from scratch. And the way it does that is it seems to modify the original path one square at a time, and it generates another path that starts at this starting point here, and it moves out one position at a time until they meet in the middle, and it doesn't make any wrong turns along the way. So it's doing some sort of interesting algorithm that can utilize the tableau of information that it computed during the previous maze solve. So chess is just one kind of problem. We have a paper on this called end-to-end algorithm synthesis where we look at a couple of different kinds of problems. One of the more interesting ones to me is chess. So there's all these, there's this website called Lichess. If you're a chess nerd, you've probably heard of it. I was excited about this and I pitched it to my students thinking they were going to hate it, and it turned out a couple of them were chess nerds and they liked this idea. So Lichess has these things called chess puzzles, and what they are is they're game states that are collected while humans play each other. And it collects a game state, and then it runs a very powerful solver called Stockfish that tries to determine whether there's a game theoretically optimal move. And if there is, then it calls that a chess puzzle and it labels it with the correct move. And if you are a human being and you don't like to go outside, then you spend your time looking at these chess puzzles and trying to figure out the move on your own. So each puzzle has an ELO rating that rates how difficult it is for humans. And we're going to consider a formulation of a problem where you give the network a picture of a chessboard, and then it has to highlight the two squares, the square corresponding to the piece that needs to move, and the square corresponding to the place that piece is supposed to move to. So we got a bunch of these chess puzzles from Lichess. We took 700,000 puzzles, we sorted them by ELO score. We're going to train on the 600,000 easy puzzles, and we're going to test on the 100,000 hard puzzles. And what we find is that if you use a recurrent architecture, you can solve about 25% more hard puzzles than if you use a feed-forward architecture. And we find that as you let it run for longer, the performance of the system increases. And it actually increases a bit when you get outside the training regime. There's about 3% of those hard puzzles that you can solve by thinking for longer. And it turns out these solvers are kind of interpretable. If you look at this chessboard, this rook, the black rook, should move down and attack the white rook. And so we expect to get a solution that looks like this, where you highlight those two squares. At iteration 1, if you try to extract the solution, it just has confidence 0.5 over everything, whether it should be in or out of the solution. So it doesn't seem to have an idea what's going on. You let it run for a while, and most of these squares start to fade to 0. But you see these kind of bright spots at the positions that the rook should start and end. But you also see these other two kind of side lobes that probably shouldn't be there. And that corresponds to an alternative move where the queen moves here and puts the king in check, but it's not a very good move to make. And if you let it crunch for a while, that secondary move eventually fades away, and it eventually gets to 100% confidence that it wants to attack the rook, which is the correct solution for this problem. Yeah, but at least in this case, it seems that you can craft a neural algorithm for chess that gets more confident the longer that it thinks, and that is able to solve a higher percentage of those hard problems the longer that it thinks. Neural nets can do other cool stuff. I'm not going to go through all the examples, but here's one that I particularly like. This is solving Sudoku. You can learn a neural algorithm that solves Sudoku, and if you train it on easy Sudokus, so those are Sudokus that have a lot of these givens, so a lot of the numbers are specified in advance, then if you let it run for longer, it can solve harder Sudokus. And so this is an example of solving a Sudoku iteration by iteration, and the gray squares are numbers that are givens, they're fixed, and then squares turn green when they turn to the correct number. If you let this thing run for long enough, it eventually fills in all the correct numbers and it can solve the problem. Okay, so to wrap up, some thoughts about thinking. Thinking systems, I think they're interesting because they can generalize to hard problems that in some sense they lie outside the training distribution, right? They're trained on a distribution of easy problems, and then they generalize to a set of problems that are outside of that distribution. So it's an interesting kind of domain shift. There's an argument to be made that maybe they're not generalizing outside the distribution. Maybe the algorithmic tools that you need to solve the hard problems are the same as what you need to solve the easy problems. And so in some sense, they're learning the algorithm, and maybe there is no distribution shift in that sense. But I don't really know how to make a rigorous formulation to ask questions about what's behind that kind of generalization. These kind of systems, they also work only by seeing a problem and its solution. There are other kinds of iterative algorithm solvers. You might have heard of things like neural Turing machines. DeepMind has an interesting algorithm learning challenge. But these challenges, the way that they typically work is you supervise each step of the algorithm. So you tell the neural network on step 1, you should output this. On step 2, you should output this. And then after n steps, you get to the end. So typically, when you do algorithm learning, you supervise what should happen on each step. And you're trying to teach a neural network to emulate an existing algorithm. In this case, we don't provide any supervision over what happens on each step of the algorithm. We just say, here's a bunch of inputs and a bunch of problems and their solutions. You have 30 iterations to get there, and then it will learn an algorithmic approach for solving these problems end to end without any human supervision over what each iteration should be. And then finally, one thing I'm interested in the future, this is a little bit ambitious, but it would be interesting if learned algorithms can replace things like Monte Carlo tree search in AI systems. So if you look at something like AlphaZero or MuZero, these systems really rely very strongly on a handcrafted tree search to play games, and they only really use a neural network to prune the tree. But it's interesting to think that it might be possible to train end-to-end systems that have those kinds of algorithmic behaviors. And that's all I have to say about generalization today. Here's some of the papers that I spoke about. Thank you very much.
Thanks, Tom, for the great talk. It's very, very interesting. So we'll have time for questions.
Yeah.
Thank you. I have a question about the guess and check algorithm. Did you try to see if the performances stay to be good with different architectures?
We tried 2 different architectures, but we didn't search particularly thoroughly. We did Linnet, and we did a fully connected architecture with, as I recall, about 15,000 parameters. And those are the only 2 ones that we checked. You could, we actually could probably do bigger architectures. After we had completed this, we realized that we could do ResNets, and they worked just fine. But our paper doesn't actually have any results on that. Big enough architectures, it starts to become, if you want to do like a full-scale Resin 18, it becomes very difficult to sample. What happens is the like concentration of measures phenomena starts to kick in, and every time you guess, you basically get the same network, and then you have to guess very, very, very many times. So we can do different architectures. Like I said, we can handle ResNets, but they're like little baby ResNets that are low enough dimensionality. One thing I'll mention is even with those baby ResNets, in our paper we check whether they can interpolate noise, so that they're not just doing classical generalization. So if you assign random labels to all of the data points, these architectures can interpolate those random labels. But so we can handle a few different kinds of architectures, but we didn't, frankly, we didn't do a great job exploring that realm in our paper. It takes a very long time to run an experiment on this, even with one architecture.
I think
it's the most expensive way you could possibly solve few shot MNIST. Yeah.
I think the idea of investigating bad small networks is also interesting, like seeing where this fails.
Yeah, the guess and check, we have to go a little bit toyish with the problem. And normally when I do experiments, I like to really focus on realistic problems. Like I'd like to use real ResNets, even if we're not using the biggest ones. But in that case, we didn't really have a choice. I can't think of a better way to do it. I wish I could, but I can't think of anything else.
Other questions?
Thanks for the very interesting talk. I'm curious about that hyperparameter, which is the number of training steps, thinking steps during training that you have in the second part. It feels like if you don't give it enough steps, it might be hard to learn things. And perhaps if you give it too many steps, it will just be slow. So I'm wondering if like you've experimented with the effect of this hyperparameter, and have you thought about formulations where like this is free and like the network is telling us when it's done rather than us fixing some.
So we've done a little exploration. This is something we didn't explore very much because the higher the number of iterations is, the longer it takes to train. In our experience, I had thought that if you give it fewer iterations at train time, then it might be faster at test time, and it doesn't seem like that really happens. It seems like at train time, you just need enough iterations that you can solve the problem, and you don't seem to gain any benefit in terms of speed from doing more or doing less, at least with the kinds of training loops that we have. So yeah, most of the experiments we did, interestingly, they all have the same training loop. They all use 30 base iterations. They all use the same architecture. And we actually didn't hyperparameter tune that very much. In fact, the way we did chess is we just took the maze architecture and we used the exact same architecture and the exact same training loop on chess. At the time we started doing this work, the GPUs, we didn't have that many GPUs to work with. And so we kind of went with the cheapest thing we could, which seemed to be the 30 iterations at train time, and we haven't explored too much outside of that. Yeah, but like I said, I don't think, from the experience we have done, I don't think that there's a substantial change in behavior if you do more than that.
So I had a question regarding, so you have all of these examples for generalization. They seem to be more problem dependent than they are algorithm dependent. So the question is sort of, should we really be studying the problems and whether or not the problems themselves have generalizing features, as opposed to, oh, this algorithm is produces generalizable results?
That's a good question. I think I'm a believer, and I know people that don't agree with me on this, but I'm a believer that there's some general principle that underlies all of these problems. And I believe that just because the same like a transformer architecture can do speech recognition, object detection, next word prediction in language, can analyze spectrograms, right? Like the same kind of optimizer and architecture can solve a really wide range of problems. And so I'm inclined to believe that there's like a general principle that's underlying all of these. And as long as you pick a hard enough test problem that you have to exploit strong generalization, and I realize that's a hand-wavy concept, you need to pick a hard enough test problem that you have to exploit strong generalization to solve it. So MNIST is actually a little problematic, and I don't like doing experiments with MNIST because even a linear classifier can do okay, and if you use second-order features, you can do better than okay. And it's not just because you've done well on MNIST doesn't mean. If you identify a particular behavioral neural network that enables you to do well on MNIST, that doesn't necessarily mean that it's important for strong generalization. CFAR, though, once you get into that 95 and up range, I'm inclined to believe that you need to be exploiting strong generalization. And so like what you're saying, it's just one example of one problem. I would hope that a mathematical theory could be more generic than that. But I like to believe that it's still meaningful to study that one problem because I hope that there's a general principle.
Thank you.
Kind of a two-part question, one for each part of the lecture. Really good talk, appreciate it. What was the architectural trick that you did to make the recurrent model better on the algorithms part of the talk, like the maze part?
You're talking about the skip connections?
Oh, was that all it was? It was like,
yes.
It was like the recurrent didn't work, it'll eventually decay, and then you had it so it's saturated.
Yeah. So what happens is that you saturate if you don't have any skip connections. So every time you run the recurrence, it reads from its memory. It comes up with some new representation, and then it dumps that back down into memory. if you do that over and over again, it's like I was saying, it's like making a photocopy of a photocopy of a photocopy. Yeah. It has to preserve all the relevant information in memory, but every time it writes back to memory, there's a little bit of noise, and eventually it just sort of melts down. Okay. If you add those skip connections, so every time I run the recurrence, it gets to see the input, it gets to see the output. Every recurrent unit gets to see the output from the previous recurrence, and it gets to see the features that were extracted at the beginning of the pipeline. Yeah. It just creates at least my intuition for why this works is that if you start to forget something, if something important in your tableau of information starts to disappear or gets corrupted, then you can regenerate it by going back to the beginning and reforming it. So it gives the neural network a mechanism to do error correction. Yeah. And it seems to help quite a bit. I mean, the difference, it seems like a small architectural change, but the difference between these two things is really night and day. It's really enormous difference.
Yeah, thanks. So the second part is about the first part of your lecture on the origins of implicit regularization. Like you said, there have been it's the popular belief, there have been numerous papers written about it. I'm thinking of one that basically, I think, proves the implicit regularization for SGD comes as a function of the ratio between the batch size and learning rate. So if you do something like that random optimizer that you did, you get rid of the supposed implicit regularization. What kind of explicit regularization did you need to do to get that full batch model to train?
Oh, okay, yes, I should have mentioned this. We do have a little bit of a flatness penalty that we use. So we penalize the size of the gradient. We penalize we have an approximation that sort of penalizes the largest singular value of the Hessian, and it forces the optimizer to find something a little bit flatter. You don't need that to get good results, I think, but you need that to get the best results, to really push up above that 95% number. And that was inspired by, like you said, there's a couple papers that predict that stochastic gradient descent has a flatness bias. And so if you run full batch gradient descent without stochasticity, if you add a flatness penalty, you do get a little bit of a boost. Yeah. And I think so there is something nice in that sense about stochastic gradient descent. And the argument I'm trying to make is not that optimizers don't matter at all. It's just that there does seem to be some nice flatness preference in a really stochastic algorithm. It's just that I think that these or create minor differences that are sort of the icing on the cake. Like I said, you can turn off the flatness penalty in our full batch SGD and you lose not very much, like less than a percentage point in accuracy. But these kind of regularizers, they do matter.
So, like you mentioned, there are these results that say that SGD is biased towards flat minimizers. Is your intuition with this volume hypothesis that all reasonable optimizers are also biased towards flatness?
Yeah, my thought is that any sane optimizer is going to be more likely to find a flat basin than a sharp basin. Obviously, that depends on the particular dynamics of the optimizer, and it's hard to make that into a rigorous statement that covers all of the optimizers. One of the problems is it doesn't cover all the optimizers. Like our poisoned optimizer does find bad minima, but that's because it's constructed to do so, right? And so I'm not sure how to characterize that from a theoretical standpoint, but it seems like qualitatively the loss landscape is structured so that any, like you said, sane optimizer is going to find the big minima. I just don't know how to rigorously define sane.
I see one more question. Last question.
And then you gave another way of sampling that local minima. Do you have any sense of how many of all of the bad local minima are the ones that you get
By SGD?
No,
no, I don't. There's an argument to be made that, I think the poisoning loss makes a lot of sense to me. You want to find a good minima you want to find a minimum that interpolates the training data but fails on holdout data. So you construct that loss explicitly. I have a loss that says you interpolate the training data and you fail on this holdout data, right? But whether that has a bias toward a particular kind of bad minima that might be different from what you would observe in practice with SGD, there may be such a bias. It's hard to say whether that's true because you can train SGD until you're blue in the face on the Swiss roll problem, and we don't really find a bad minimum. It does, yeah. That's a good question. I guess there is no real hard distinction between the two, right? So guess and check, it will land in any basin with a probability proportional to its volume. So if you find a poison minimum, you could compute exactly what you could do that integral, and you could compute exactly what the probability is that the guess and check optimizer lands there, and it would be non-zero, right? I guess the question is more, how different is the distribution of things you land in with SGD than what you land in with guess and check? And I guess I don't know what the answer to that is. My intuition is that trying to compute the size of that difference would be really hard. But yeah, we don't have any, we haven't done anything experimental to try to control for that. I can't think of any good way to control for that factor. That's just a fundamental way that SGD might be different than guess and check. Yeah.
Let's thank Tom again. So this concludes all the talks this afternoon, and thanks again for all your participation. And I hear a lot of good conversations going on, and let's continue that in the poster session. So it will happen at 5 p.m. in 15 minutes in the other room, as I mentioned, and let's keep the vibe on. And thank you a lot for the participation this afternoon.